All your videos work, Nick?
I figured you just weren't sure. It was a pretty big file.
Yeah, it came through. The way I described to everyone, you worked so hard for the last 4 years, so really excited to see your final projects and your results, your prototypes, your testing. A lot of hard work went into this. So.
Very good. Welcome. This is kind of an exciting time. Next year we will have all integrated senior projects. Dr. Bendars and I have been working this issue. This year we do have some EE-only projects, but I think we look forward to a combined, realistic project to get to project scenario so you get a better understanding of what it's going to be like when we get out there to this bad world. We have to work with a lot of different people, a lot of different disciplines, and that's a good thing. So welcome, and thank you.
Okay, so you see our schedule. Thank you to Suzanne for printing them out. They're available all over the place. We're going to really stick to the schedule, so each team, please stick to your 15-minute time limit. I'll be right up front timing you. I'll give you a 2-minute warning when we get close, and then we'll have up to 5 minutes for questions from the faculty. And you see we have 3 teams going in our first block this morning, then a quick break. We have coffee, some snacks out in the lobby. Thank you very much to Suzanne. She has coordinated everything to do with the food and the filming for today. So, and then we have 3 more teams coming up, and we have a nice lunch with boxed lunch, and then our last teams. and our wrap-up, so we should be definitely out of here by 2. All the senior projects 2 teams are going first, and then we have 1 senior projects 1 team going at the very end. So I encourage everyone to stick around for the entire time. And my last announcement, I have all the teams' PowerPoints loaded, ready to go. So when it's your time, just come right up and you could just load it. I checked the videos should work fine. Okay, so yeah, let's get going. We're going to kick it off with quantum.
I'm gonna check the video real quick. Okay, we're good. Joe, switch it. Oh wait, yeah, I'm back here until you. Okay, yeah. It'll be fine if we don't have it anyway. All right, whenever we're ready.
All right, good morning, everybody. Thank you for being here. We are Group 3, otherwise known as the Quantum Rehab Group. My name is Alex Lunar. Like that.
Tyler Draken.
Christian Dietrich.
Joe Kowski. So, getting into a little bit of introduction to our project, just at a base. So, we work with Quantum Rehab on this project. They're a division of Pride Mobility. They have a wide range of power bases, which specifically tailored to a customer's needs. Some terminology we'll be using throughout this presentation, such as power base, that just refers to the power bottom of their wheelchairs. The controller is the device which a user can use to interface between themselves and their power base. So this is the current QC test fixture at Quantum in Area A. Currently the fixture runs to check the wheel speed, make sure that it reaches its maximum speed, along with the battery voltage, make sure that's correct, and also checks the interface between the controller and the power base. So for example, an operator can turn the controller to the left and make sure that the wheels will turn the correct direction for the power base to turn left. So for our project scope, we started out looking to remove all decommissioned hardware from the machine at Quantum. However, by the end of last semester, we worked with Quantum and refined the scope to 2 major deliverables, those deliverables being a complete drawings package for Quantum and a proof of concept, which will show the improvements to the speed and the turn test. And now moving on to some requirements that we had for design. So for the capabilities for the speed test, the speeds have to be detectable within 3 to 8 miles per hour, and that has to be for wheel diameters of 10 to 14 inches. For the caster test, we tested both the front and the rear casters simultaneously on a front and a rear conveyor, and the caster should not slip on the conveyor belt. And then for general workflow, each test must take less than 6 minutes and must be at least 120 tests per day on the machine. And for the operator interface, the visual test will still require a accept or reject from the operator of the machine. However, all numerical values will be automatically recorded by the PLC, so those can be uploaded to the QC test database and recorded there. So that will be for the speed test, the voltage test, even the turn test, where signal will be sent to the PLC and can determine which direction to turn. Now that really is some foundation for what the project actually was. We can talk about how the project was managed across both semesters. So on the screen right now is our WPS. This is just a graphical representation of how the tasks were delegated out to individuals. Mechanical design was handled by Joe and Christian. The electrical design was handled by Zach, and the automation design was handled by Tyler. I handled the majority of the drawings, the reporting, and all of the other auxiliary tasks. So this is the schedule. This represents the second semester, which takes us from the build phase that began in February all the way up to culminating with the project report today. And this is our budget. This is just a simple representation of what the prototype here cost us. The school allotted us $500. We were fortunate
The big ticket item was the metal. The rest of it was essentially the circuitry needed for the electrical design. Now that we've kind of talked about what the project was and how we managed it, we can take a look at the results here, the design. This is our design that we presented to Quantum. So this is just the fixture part of the QC test from slide 5. That would be the part that the power base section sits on. Some of the mechanical design changes were an addition of the conveyor to the front of the fixture. This allows the front anchor casters to be tested simultaneously. We also added a belt cleaning system consisting of brushes underneath the conveyors and then collection pans. This helps promote a clean work environment for the operators in this home.
So moving on to the electrical upgrades. One of the first upgrades we did with our design was the incorporation of a rotary cooling device. What this encoder allows us to do is measure both the speed and direction simultaneously just using one sensor. That was the first upgrade. The second upgrade was the use of a PLC. What this did was work in conjunction with the sensors in our circuitry, took those output voltages and readings, and did the appropriate computations of arithmetic to produce meaningful results to user interface that the operator would see in real time, such as the speed and the direction. Our last upgrade was the addition of a stack tower, which provides just visual aid on whether or not tests work based on a green light, red light scheme. So test passes, green light, fail, it was red light. Moving on to the prototype we developed this semester. So based on the schematics we developed in the previous semester, this is what we designed here on the breadboard. And we're testing right now with a little mock setup here. We have our encoding device on a shaft that's rotating up and down. That's how we're testing the integrity of the rotational direction circuitry. And this right here is the same circuit, but it's a little bit more refined. Besides some errors with the first circuit, there's some flaws. We tried to iron them out with this revised version. Once we determined that this was adequate enough for our needs, we moved this to the PCB board, which was the finalized circuit we should be using our testing fixture.
So continuing on with the prototype, on the far left is our current fixture test frame, which is shown here. Figure 19 shows the bearings that are attached to the rollers and shafts. And then finally, figure 20 is the prototype with the quantum power base attached to it. Going into a little bit of the mechanical specifications. So right here in figure 21, we have the frame schematic with dimensions of 41 inches in width, 31 1/4 in length, and 6 inches in height. Other drawings that are not shown because they were from a master car are the rollers, shafts, and bearings.
As far as the electrical specification, what the board we designed our circuit to run off of voltage between 18 volts and 24 volts. It can be no more, no less, for proper operation. For our output voltages, specifically the frequency of the voltage output, which is analog, we conditioned the signal to be capped off at 10 volts. This is mostly from the PLC because the inputs from the PLC, the analog section, it can't exceed 10 volts or else we risk harming the PLC or causing a malfunction with it or it can't be read.
Moving on to the PLC. The PLC we were able to acquire this semester was a Micrologix 1100, allowed to be used by Dr. Zhu. The PLC comes with 10 digital inputs going up to 120 volts AC and 2 analog outputs ranging from 0 to 10 volts DC. It also has 6 relay outputs. For the PLC code, picture shown is a copy of the main program we have. After you would start the program, it would then cycle down to the subroutine of the speed test, where it would take the base's wheel diameter and go through some calculations, as well as take the input from Zach's circuit, the analog input, do some calculations, and it would determine the speed of the base. It would do this for the left and the right, compare the two within a 5% tolerance range, and then determine whether or not it passes or fails. If it fails, it would need to be reworked, but if it passes, it'll move on to the next test, which is the turn test. Basically, if you would turn it right and the base was turning right, it would show a green light, and left, vice versa. But if you would turn it left and it was showing right, then the base would need to be reworked.
So moving along into the testing phase. So for the test process, from the mechanical aspect, we individually took each part of the system and performed stress analysis on it. For the electrical aspect, we tested the circuit using a function generator as the input, and then verifying the proper output voltage. For the PLC, we tested through simulation in the program with like some dummy variables with what we were expecting, and got results respectively. For our trip to Quantum this past Thursday, our speed base, the quantum power So here's a picture of the mechanical stress testing on the shaft. The shaft eventually did fail at 1,000 pounds, which I will show in the table in the next slide. But the components that were tested, as I mentioned, the square tubing, the shafts, steel rollers, and the bearings. And here's that table with the shaft testing results, and with the red fail at 1,000 pounds and verified by myself.
Okay, with the circuit validation, verified that these circuits work. With the speed test, what we did was, as Chris said, we used a signal generator to verify that it was working. The idea is when a rotary encoder, when it's in motion, it's outputting a square wave. And when this encoder is going faster and faster, the frequency of that square wave is increasing, right? So instead of just turning by hand here to maintain a constant wave, we just use a signal generator to accomplish this. So we fed that to our circuit, we measured the voltage at the output, and based on that voltage output, we could actually determine an approximation of what the frequency is based on that. And then we figured out the frequency based on that voltage output compared to the actual frequency entering that I see, and that's how we determine accuracy. So for example, we had a square wave going at 3K right there. According to our IC, we're getting an output voltage of 1.97. Based on that, we derived a frequency going to the IC of being 3,000 and 5.22 with an approximate error of 0.17%. And we did this for a wide range of different frequencies to see if the accuracy is consistent with the rest of the frequencies up and down.
Previously mentioned by Christian, this past Thursday we went to go to Quantum to perform some on-site testing. We were able to perform 2 different tests. Unfortunately, we had a small issue where the rotary encoder we had planned to use had failed, and we had to substitute for a different style rotary encoder. So our testing proved that we had a 10% error with the new hardware implemented. This is the data collected from the first test phase. The second column from the left shows the input voltage that was output from Zach's circuit. The middle one shows the mileage of the PLC that was created through the calculations. The fourth column, it shows the speed that was output on the base's controller joystick, and the far right shows the percent error, the percent difference between the two. And this data is the second set of data collected. We do have a smaller average percent error, and this is due to the fact that after the first round of testing, we performed some fine-tuning adjustments to correct any errors with the new rotary encoder. And then here's a quick video of our testing. Conclusions. After we're done with this presentation, we plan on giving Quantum a complete drawings package as well as a complete schematics package and a copy of the PLC program that we have created. The testing confirmed the concepts of the speed and turn tests were successful for the scope of the project, and through the utilization of a oscilloscope, we discovered that the new encoder presented a much lower frequency than was initially anticipated from our initial design. And here this list shows the applied courses utilized throughout this semester and previous semester for this project. On the right shows the mechanical, the left shows the electrical, and the bottom center shows all of the general engineering courses.
So just going over a little bit of the ethics, the main one for everybody, conduct oneself as a professional. No falsify data, only work in areas that you are qualified to, etc. And some final thoughts?
So this project was the primary focus of the group for the last 2 semesters, and needless to say, it was quite a journey. So along the way, we learned some pretty good lessons. The first is that real industry projects are consisting of team members that have different functional roles. And it's very important that
on the stress analysis, do you do any fatigue analysis? If it's going to be in operation, like under load, on load constantly?
We did not perform that. It was really just the stress analysis. We should have probably taken into account for that. There definitely were some other things that, in all honesty, the whole group could have taken into account for.
With the stress analysis, what is the safety factor under what's generated?
Don't quite find it. It said it in the simulation.
It's 5.
Was it 5?
It's 5.
Could you move back to your left side, please?
What side?
One more. One more, please. One more, please. Right here, right here. Okay. So you see there at the bottom, that's, I mean, that really caught my eyes. Because, I mean, you see there, what you can observe is far below the minimum required for this application. I guess, I mean, what's the purpose of PLC here? Why do you use PLC for this particular application?
This is just what the company requested we use. So.
Because usually, normally PLC are not used to handle this kind of high frequency. I mean, that's like at least 1 kHz to see that for this particular application.
Well, no, we're not sending that frequency to the PLC. We're converting that to a voltage, and then this voltage, there's a conversion formula to cover that, approximate frequency that's CDIC.
That's like you're detecting that kind of frequency, right? That's your application frequency, right?
Yes.
So that's what I'm trying to say, because PLC is normally not meant to handle that kind of high frequency. It's relatively speaking a low frequency device.
No, we have an IC here, right? You have a signal coming in, going at some frequency that we don't know, right? This IC is taking that frequency, it's converting to a voltage, right? This V out. Your V out is going to equal to your R1C1 times your supply voltage. Based on parameters we already know.
Exactly. I know what you did. My point is, I mean, for you, what I'm trying to say is that there's a very good chance that for your application, the PLC was actually bottleneck. That's my point here. It's just like for you guys, actually all you need is design a small microprocessor based like just small display, and that's all you need. Why do you have to send the signal to PLC? Because you're not really doing control here. You're doing a measuring device.
Well, and that was requested by Tom. We use the PLC because that's what the company wanted to use. And then some of these issues did come from our coder. Zach can elaborate a little bit on it.
Yeah, the discrepancy you see here, why you're seeing such a difference in frequencies, that the original encoder we were using here had 500 counts per revolution, right? When that died, right, burnt out, we had to get another encoder. And the encoder we got here was 100 counts per revolution. It was producing a frequency that was far lower, and it's resulting in that 0 to 600 hertz, which messed up our entire circuit. We had to go back and reconfigure those parameters that adjusted incorrectly the circuit. We just didn't have time to make those adjustments. That's where we're seeing so much error.
Yeah, so we're going to continue along this little thread, if you don't mind. And that, one, the main project was you're doing obsolescence mitigation. You're removing obsolete parts and coming up with a new system for that. The problem that you encountered with the encoder dying and you having to replace it is very similar to the obsolescence issue. You couldn't get the same encoder, so you had a change in the curve. Okay, you should be able to correct for that with calibration. And so now I look at what you have here numerically, and you had your other tables and stuff that you showed. And the question I have is was the error between the set speed limit, set speed on the device versus what you were reading for all of the different miles per hour points that you were looking for, was that linear? Was it the same? So I saw somewhere you had it set at 4.5 miles an hour and you were reading 4, and so on and so forth. Was there linearity? And did you have the resources in your software to create a calibration table to put correction factors in?
What happened was this encoder that you're seeing here, this was operating a range that was non-linear, it's exponential. That's why you're seeing such weird outputs. But during our testing here, we were operating linear, range. That's why that equation, V out equals this here, is applied. It's linear.
But was it repeatable?
Yes.
If it's repeatable, then you should be able to calibrate it out. Right? Okay. If it was repeatable, in other words, every time you set it to a particular speed and you were always getting the same error, if if you keep doing that over and over and keep seeing the same thing, you should be able to calibrate that out. Right?
No, we did try to do some experimentation with introducing multipliers into our software to account for that 10% discrepancy. But
It's not, you're not going to do it with an equation.
yeah,
You're going to do it, we're going to do it with a correction table.
Okay, thank you very much.
What?
It's reading like a dream.
Where's the presentation button?
Good? Okay. All right. Good morning, everybody. I'm Andy, and this is my colleagues, Mateo and Sarah, and today we will be presenting our research on the IoT wearable. Just a brief overview of our agenda for this morning. We're just going to talk a little bit about problems and objectives of the IoT, project requirements, constraints and specifications, deliverables, a project schedule, hardware development, software development, 3D printing, project outcomes, some of the challenges and successes we encountered along the way, risk, opportunities, lessons learned and suggestions, courses we utilized, and some acknowledgments that we'll find to conclude the Q&A. All right, so health monitoring devices for seniors are expensive, and they often require subscriptions and require user input for emergency alerts. And what we set out to do is create a proof of concept for a cheap single purchase passive monitoring alternative to current health monitoring devices on the market. Some of our project requirements, first and foremost, this is to be interfaced through an application. It was to be able to communicate with Bluetooth, monitor heart rate and fall detection, capable of alerting emergency personnel or personal emergency contacts during a medical event. This is just some of our project specifications. It's clocked in at a total weight of 65.2 G or 2.3 ounces. A risk case footprint, which is what I have right here, of 6.5 by 4 by 3.3 centimeters. A finger case of 6 by 2.5 by 2.2 centimeter, and a battery life that lasts greater than 6 hours. This is just some of the project constraints we had to work around. First and foremost, obviously, it must remain fixed to the user's wrist and finger. Weight and size was a huge factor. No one wants to look around a huge 10-pound device on the wrist all day. Wire lengths going from the wrist case to the finger case had to be appropriate length, just so it fit properly. And it must have a long enough battery life for daily use, because if this thing only lasts a few hours, it's no good to anybody. Next slide. And this is just a brief list of deliverables. Hardware, in the end, we decided to go with Adafruit. Software was done in the Arduino IDE environment. We had a 3D printed finger case, which houses the sensor evaluation board, a 3D printed wrist case, which houses the Arduino board and battery. And for a phone application, we decided to use Adafruit Bluetooth Connect on iOS. And this is just a brief overview of our project schedule. In January, we set out to fully understand sensor operation. In February, we started to play around with Bluetooth connectivity and began coding the sensors. In March, we concluded coding the sensors, and we began 3D printing enclosure designs. And in April, we finalized our 3D printing enclosure designs. We implemented the hardware into the 3D printing enclosures. Then we tested all components together to ensure they all worked correctly. And now I'm just going to give a very brief overview of the hardware development. So this is just a preliminary block diagram. Starting on the left here, you have a software program which then interfaces with a microprocessor, which is powered by a battery, and it may have some pertinent battery circuitry, such as BMS or voltage regulator if it's required. Then from there, this communicates to a set of sensors, in this case a heartbeat and gyroscopic sensor, and those signals are sent to a measurement amplifier, which is then fed back to the microprocessor. Adding actual real-world hardware, we end up with, in this case, the Blue Fruit Connect app talks to a Adafruit Feather Express microcontroller, which is powered by a 400 milliamp hour battery, which then communicates to an Adafruit accelerometer board and a Maxim sensor evaluation board, which then goes back to the microcontroller. If you just briefly look at this, we mentioned this has to communicate over Bluetooth, so why is there no antenna here? Well, in the very early stages of this, we did set out to develop a antenna that would meet IEEE standard on specific absorption rate, but we later on decided it would be a little bit easier just to include all this in a pre-assembled design that meets those standards already. Slide. This is just a slide just showing the hardware flow, just to get a better visualization. Starting on the top left, you have the 400 milliamp battery, which then powers the Adafruit microcontroller board, which is on the bottom left. From here, this interfaces with a perf board that's sized correctly, which interfaces through some header pins. Then from here, you can just solder the perf connections to a wiring harness, which then terminates out to the Maxim sensor evaluation board, which you can see at the top right. And this is just a brief overview of the hardware costs. As you can see at the bottom, the total came out to $46.67, which is well under budget I think our budget is $500.
I'll be talking about the software part of the project. This is our software flow diagram. As you can see, as it turns on, the sensors, the evaluation board is reading heartbeat and SpO2, and as it measures, it's asking it if it's normal, and if it's normal, then it says okay at the output, and if it's not normal, it'll say abnormal, and it's a complete cycle sending in notifications and then back to point A. As we wanted to improve the project, we wanted to put an accelerometer on it to measure fall detection. This is what the Blue Fruit Connect app looks like as it's giving us our output. As you can see, it has the sample time, the SpO2 rating, the heart rate, and then the flagging we had as it was normal or abnormal. As it's over 120 BPM, it's tagged as abnormal, and if it's under that, it's tagged as okay.
Now on to the 3D printing portion of the project. Here you can see the first couple of revisions for the risk case. Each of these had problems which we ironed out, which we can go into further detail on upon request. And on to the finger case. This gives the same information, and you slowly see the revisions take form until, next slide, we got to the final revision. With a little bit of hard work and teamwork, we were able to come up with the design optimal for both assembly and use. And next slide. The same can be said for the wrist case. This design is noticeably taller than the previous designs. This is a result of the header pins previously mentioned. These pins created extra distance between the perf board and the Adafruit board. This resulted in a massive increase in the ease of assembly, particularly at the soldering step, so we decided to take that trade-off. And here you can see the total costs associated with this portion of the project. In red are all of the portions of the project not used in the final iteration. The total in the bottom shows everything we spent, while the final product cost shows everything necessary to create the final design. And on to project outcomes. Here you can see the completely incorporated version, including both the hardware and the enclosure. And in the bottom left, specifically, you can see the blood oxygen and heart rate sensor sitting flush with the finger case lid, allowing for constant readings and therefore passive monitoring. And here, you can see me very shamelessly enjoying the products of our hard work. First, my resting heart rate, about 30 minutes after a cup of coffee. I'll begin some light activity, which a moment later is flagged, or not flagged, but you see the noticeable increase in heart rate, and then some more moderate activity, which again a moment later results in a flagged abnormal heart rate, and a moment of rest results in heart rate flagged as okay. And so on and so forth. And here you could see the results of our data collection. In the cooler colors, you could see the results garnered from a pharmacy bought pulse oximeter. And in the warmer colors, you could see the results garnered from our project. On the left, you could see blood oxygen readings, which again, you could see a large variation between the bought sensor and the design sensor. As a result of that, as well as us having no safe way to alter our blood oxygen, we decided to exclude a blood oxygen tag from our safety tags. But on the right, you could see the heart rate tracking much more closely, with each of the cool and warm colors paired based on activity level. Specifically at the very end there of the top line, you could see it dragging down. That was after a deliberate moment of rest to test that it would indeed tag that as normal, and it did. And as for the total project cost to create our final design, we're at $65.65 of the allowable budget of $500.
So some of the risks we had going into this project were the 3D printing tolerances, the 3D printing enclosure durability, because you wanted something to last long because it's going to be on your wrist. The cabling strain relief, because you don't want the cables being tugged the entire time, and then the sensor inaccuracy. Some opportunities you could do going forward, you can implement fall detection with the accelerometer. You could shrink the enclosure so it's less weight on your wrist, and doing that you could use a smaller battery. You could also develop your own iOS app that'll send notifications as to having flagged abnormal. And then we also wanted to implement wireless charging. So some of the lessons we learned during this project is stay with the established hardware. We did switch our hardware a bunch of times, and so we finally settled down with the Arduino. Better anticipation of challenges of the prior knowledge we had would have been nicer, and then time management. These are the courses we utilized during this project: Intro to Quantum Computing, CAD Lab for 3D printing, Embedded System Design, which was for the board, and Digital Design and Scientific Programming for coding. And we would like to thank our advisor, Dr. Sabuni, our project manager, teacher, Professor Taylor, and Dr. Mu for our 3D printing guidance. Thank you. Do you have any questions?
There were slight cuts made, so we kept the sample times in there, but there were slight cuts made because there were moments in which, due to...
Heartbeat went from 68 to 88 to 150. How long was that period?
Sorry, what was that?
Your heartbeat went from 68 to 88 to 150.
Yes.
How long did it take for that to happen?
That was about a 30-second interval.
Okay, so there's either something wrong with your device, or you should show yourself to the cardiologist immediately. You look healthy, so I assume it's the former.
I'm
Those numbers don't. 150 is a very hard heart. Like even under very intense exercise, somebody at your age, 150 is ridiculous. Going from 68 to 150, unbelievable.
That's fair. Yes.
So a follow-up to that, you said you compared it to a commercial off-the-shelf item from a pharmacy.
Yes.
Did your numbers match them? Or
Yes, so actually, do you want to go down? Down? Up?
Up.
This is the table version of the chart the chart of the table we showed earlier. I mentioned before the blood oxygen was way off. We killed that tag completely. But the heart rates you can see matched rather closely. That one that was shown before was probably an outlier, I must say.
Dr. Kerr.
Yeah, leaving this table up, it goes back to calibration. You know, this is a calibration event that you have to deal with on the system. So I'm assuming that you didn't do any of it. You were presenting raw data that you were measuring, but you have no means of calibrating out
something that's much cheaper and is specifically for this purpose.
Okay. Because the Apple iWatch has all of that, and that was what I wanted to hear from you. In other words, you want to make it so that it is affordable to others, as opposed to going out, somebody having to go out and spend hundreds and hundreds of dollars on an iPhone.
Did you, when you presented the heartbeat results, is that SpO2 accelerometer?
Sorry, what was that one?
The SpO2, what's that?
That is the blood oxygen level of your.
Okay, so did you test the flow? Were you able to test the flow? There's you have to test the flow, a flowing. What's the purpose of the accelerometer?
Oh, so we initially planned on implementing that as a factor which we would tag for abnormal events to show like a abnormal health event. We showed this to show why we cut that feature despite it being inherent in the board we were using. Because there's a several point difference, which that could be the difference between someone completely healthy and dying.
So you didn't include the results of the accelerometer at the end?
We do not include it as a flaggable event. There's no output to the SpO2, however it reads out.
But were you able to detect the flow at the end? You mentioned you were able to detect the flow.
The accelerometer.
Oh, the actual fall.
Yeah.
No. So we ended up cutting the accelerometer. That's something we want to implement in the future of this project.
Okay, so because that's what I guess I'll ask you a basic question. How would you detect the flow? So based on the accelerometer, that's going to be almost impossible. How would you, just philosophically, how would you do that?
So the initial idea was actually brought forward to us that upon incurring the fall, your heart rate will skyrocket.
No, not even 2 seconds. I mean, did you ever conceive that idea? Like, what's the concept to detect flow? Like, what kind of power would you need? What kind of sensor information would you need to be able to?
We had a specific algorithm we intended to implement. The initial idea was a 45-degree change in orientation.
When you count that on my wrist, that's easily 45 degrees.
Yeah, we're going to go with a very small sampling time, and also this is for elderly individuals. So that is a downfall, but also this could be tagged to, since this is meant to be an IoT device, it could be daisy chained with a series of other devices. One could be attached to the torso, for example.
So you didn't convince yourself, right? That concept that would never work, right?
It would be hard to implement, but I'm confident we could find a way to do it.
Okay, thank you very much.
Well, do you want to go to your video quick? We can check. This is like the volume.
Maybe they didn't. Maybe they did not have sound.
Check yours real quick.
Yeah, I don't hear it.
Projector control volume. Can you see that? Microphone volume. I don't see it like moving.
Let me try doing this. Oh no, that is with that.
See if it works. See if it goes. I'm like trying to put the speaker on.
You hear it now, I would think.
Oh,
it works on the computer.
switch behind you. Flick it off.
That one.
Give it a couple minutes to warm up.
Thank you.
Thank you. That one might be really loud. Do you want to
Yeah,
lower the
we're gonna
volume?
turn it down on that.
Lower the volume just a little bit.
Probably lower than half.
Because it's going to be loud.
It's very
for us.
loud.
Very loud.
I know the speakers in here are good.
Do you want to give?
Yeah, we did.
Do you want to give it a test again? Or?
You want to give it a...
You said let it, Dragon said it'll warm up. I don't know, we can start calling.
Is it Dr. B?
Just a couple minutes, I guess. Technically.
Because I have,
There we
There
go.
we go. That's on the business.
So that if you need to go.
Okay.
Okay, perfect.
Don't want
Thank
it
you.
to be too loud.
Pass. Beginning.
Do you want to introduce us? Like, we'll do the team.
Yeah,
Team one.
I'll do like the team and then we say it. All right, good morning. We are at Home GT, and here's a presentation on our senior projects that we worked on the fall and the spring. My name is John Tugend,
Patrick Seeley, Andrew Lamb.
and our advisor is Dr. Gamari. A little bit of a summary of our recap is we saw that there's 12 to 15 million cars junked, and 34% of these have a turbocharger. We said, what could we do with this turbocharger to keep it in focus and maybe do a little bit of recycling while at it?
So what is a turbocharger? A turbocharger is a purely mechanical device that is used to boost the power output of internal combustion engines. The turbocharger works by having two housings. It has the compressor and the turbine side. Air flows through the compressor side into wherever the combustion will happen, and the exhaust gases from the combustion will flow into the turbine and exit the turbine housing.
So as Andrew just pointed out, as we went over last semester, the turbocharger has the two main components of a gas turbine, so that's what we decided to build. As you can see here in our prototype. Quick disclaimer, this has been done before, but it's mostly just been a trial and error experiment. So the scope of our project was to build one with actual numbers on power output so people can effectively see it and know what they're buying and have it for at-home use, pretty much.
Our requirements were we wanted to keep it at about $750 per unit, and it should be no heavier than 150 pounds. It should be able to produce at least 13 horsepower power to be able to compete in the market. It should last for about 500 hours at max power. It should be simple operation. It should be safe to use.
So here we just have the basic design showing the flow of each subsystem. You have the fuel system in the red, you have the electrical system in the yellow. In the middle, you have the combustion with the airflow going through the turbocharger. And then in the purple, you have the oil and lubrication and cooling system.
So last semester on the design part, pretty much the most important component we had to design was the combustion chamber. So here's our final simulation for the fluid ANSYS. You can see the velocity magnitude profile, ensuring that we had a very stable profile to house the plane.
Back when this was in theory, we came up with this design for our turbocharger, and as you see, we're able to stick to it pretty close.
So here we just have the overall dimensioning weight. On the right, we can see the table showing the weight of each part, and then it came out to be around 140 pounds in total, which is about 10 pounds less than we originally estimated.
And this was pretty much at the end of last semester. This was our final package we came up with in the design. These are the main milestones we would try to reach throughout this this semester. And pretty much as we move on now through our testing and results, we'll be able to point out each of these and see how they either changed or how closely we were able to meet the requirements here.
Our work breakdown schedule is shown above. We were able to stick to it to almost a day for every single process.
Here we just have our budget. We're showing the cost of each part and the distributor and also the shipping fees. We also had some factors that kind of popped up, which is our turbocharger having to come from a different distributor because it was sold out, so it cost a little bit more. The need for another fuel regulator and then some shipping fees as well.
So moving on to the content of this semester, pretty much here we start with the prototype build. There's each of the team members in action. And the main components were to build the cart essentially, then the combustion chamber on the turbine, and then each of the three subsystems, the electrical, the fuel, and the oil and cooling system.
So our combustion chamber was comprised of mostly scrap that Mitch had downstairs that we were able to fabricate into being useful. Figure 15 shows the outer housing for our combustion chamber, which was used from an old helium tank. We didn't need the gold lining on the inside, but it made it look pretty. And then down in figure 17, you can see a mill cap that Mitch milled out for us, then we helped along the way.
Here we have some other parts of the combustion chamber. We have a flame tube, which is a 16-gauge exhaust tubing. As Pat mentioned earlier with the anti-fluid simulations, we were able to figure out the correct placement for all the holes and the sizing for each set of holes. In figure 20, you're able to see the adapter that we use to connect the combustion chamber to the turbine for the exhaust gas. To guide the exhaust gas into the turbine. We also have the elbow that is welded to the outer tube, as well as the boost pressure gauge and the rubber elbow that leads from the compressor to the combustion chamber.
And so once the gas turbine itself was completed, these are the three subsystems that had to obviously go along with it. We have our electrical with the spark plug and our 40 kilovolt spark generator. Our fuel system, you can see there's two tanks in parallel. We initially started out with one, but we'll get to the details of that while we have two. And finally, our oil cooling system. And you can see the flow path. It would take either up to the turbine or where it bypasses simply to just cool the pump in the process.
So after talking about all these subsystems, we wanted to make sure all of these were functional before we added heat into the equation because we didn't want to ruin the turbocharger because they weren't going to let us buy a new one. So we checked our oil pump for functionality and found that it was going to run from 10 to 50 psi with minimal leakage. Our cooling fan is oversized, which is great, kept the oil nice and cool the entire time. Our ignition system was able to give us a continuous spark, no problems at all putting that up. And for our open flame stability, we had minimal turbulence with no liftoff present, so that was very good for once we were about to hook it up to the combustion chamber.
So here we get, as John said, we put the components and subsystems, and now we finally get to our first startup. This is our first test, which we usually do to make sure that the system is able to run and ignite, as well as get to idle as it runs. Some key features are that we use a single propane tank. We had a 1-to-1 nozzle to make sure that the exhaust gases are let farther away from the complete system, so we don't have any heating of unnecessary parts. We had a plastic oil tank, as well as the oil pump running at about 30 psi. And we have a little video here showing our first test.
So with the first test came fortunately some good successful results. The goal of that was pretty much to start up and see if it would self-sustain, which it did. So that was very good. It lasted for about 2 minutes until we accidentally turned it off. But it also confirmed the calculation pretty much would it work, and at least it worked. So that was really successful. However, a few unacceptables. It took 15 minutes to start up, and one of our requirements was easy to use. So that obviously had to be handled. We had to worry about that. There was minimal power output. Pretty much one propane tank only delivered enough fuel to just reach self-sustaining. And then there was a turbo oil leak, and we had no reported data for this run. So we had a bit to do moving forward.
So as Pat stated, the unacceptable, for test 2 and 3, we made some modification and updates. We added on that additional propane tank to add on to our fuel input. We changed out our oil reservoir from the plastic container to a metal container, which was way more durable. We lowered our oil pressure down to 20 psi, and we added in an oil temperature gauge to make sure that we weren't running into any problems there. And we incorporated 2 to 3 exhaust nozzle to maybe give it a little bit more power and more oomph. So from this test 2 and 3, we were able to get successful results from our changes that we applied. We were able to get the oil leak under control. We were going to be able to get potential power output, and we were able to start up in about 5 minutes, which includes setup from all of hooking up the propane tank, making sure we were in a safe area, making sure we had the fire extinguisher. And the test we ran the first test 2 for 7 minutes and test 3 for 12 minutes.
Test 3, we were able to use Dr. Marr's high-speed camera to take captures of the pressure wheel as it was spinning and the full system was running. We were able to take 4 captures at 2 different boost pressures. We had 1 capture at around 0 psi boost, equivalent to, and then we have 3 captures at around 2. We were able to take the frames per second and frames per revolution from the captures, and we were able to calculate the rotations per minute. As you can see, the capture right here of capture 3. Using the compressor map from the distributor of the turbocharger, we were able to find that the turbine efficiency for capture 3 was about 68% with a mass flow rate of 0.2 kilograms per second.
Then moving on to our final test we did, essentially everything remained the same from the previous test, with the exception that we really played with the fuel flow. Instead of having a low pressure on the regulator and a large orifice on our main control valve, we really opened up the regulator pressure and had very successful results. We essentially went from a boost of 2 psi to 9 psi, which is about 30% of what the turbo can handle. So it confirmed that we were running at about 30% of the turbo's capabilities, which is what we had actually anticipated later on down the road. And also the max fuel flow at 0.91 grams per second was approximately at the 30% mark as well. So that was really good that the 2 of them lined up. And here's the run there. We're operating at 7 psi boost.
So from this test, we were able to apply that to our formulas we had, and we were able to come up with graphs. So utilizing our pressure ratio, we were able to solve for revolutions per minute, and seeing that it's a linear relationship between our pressure ratio and our revolutions per minute increase. And then we were able to use our RPM to figure out our mass flow rate, and we also have a linear relationship as the power is increased on the system.
Here we have some more graphs as well. We have the exhaust gas temperature as well as the decibel rating graph showing it for the operator. In the exhaust gas temperature, you can see the red line showing the max turbine housing temperature. You can see that the first point is above 700 degrees Celsius, and that point is because of initial ignition. As we have more fuel in to start the ignition to get the system running, but as soon as the system starts running, the exhaust gas temperature does decrease as well as the pressure ratio increases. For the decibel rating for the operator, you can see that there's 2 lines as well, the red and yellow showing OSHA recommendations for ear protection. You can see that our system runs mainly over 100 decibels, which means that you should probably use ear protection during the whole time that the system is running.
And finally, here we have our energy output from the exhaust gases. So obviously, the small assumption here, we were assuming that all the exhaust gases were air, which in our calculations was approximately 80%. So it should be a fairly good approximation. We were able to determine the enthalpy, and from there, our exhaust energy output. And so there on the right, you can see in the table there, you can see the energy output in kilowatts, which is providing a user with pretty much the information they would need to know how much power they can draw from it, essentially, depending on their applications.
Here's a slide with our references for what we used. We used the main reference we needed was we got the turbo for SolidWorks off of GrabCAD. We would like to give a special thanks to Mr. Mitch Adams, Mrs. Suzanne Stash, Dr. B, Dr. Gamari, and our MA 392 classmates for all love and support. Are there any questions?
No questions. Oh my goodness. 13 horsepower, how many kilowatts is that?
So the 13 horsepower was the cost, that's what it would cost. The budget that we were working with
what anti-aquatic gasoline engine for that approximate equivalent amount is the horsepower that we provide. So that was the number we set our goals to. If you go back to the energy slide, that is significantly higher. So it's not directly power output, it's energy output. So it can potentially be converted into the power, but it is, most of it is in the form of heat and not pressure. So it's most of the test runs there are about over 100 horsepower. Technically, you can convert all of that to power, but obviously the efficiency would be very low because it's mostly just polyphenols gas with very low pressure.
Yes, we were able to find a conversion table that 1 kilowatt is approximately equivalent to 1.34 horsepower.
Efficiency, how good or how bad is your system comparison with conventional customers?
So obviously, because of the boost pressure, it's only running at a pressure of 9 psi. So we're not even running at a pressure ratio of 1:2, which it's not a very efficient combustion. But in the event, so we were only able to run it at 30% because the propane tanks could only deliver that amount before they would just give out. So if we could have used liquid fuel and provided enough and run it at a higher boost, it would have been much more efficient combustion.
Obviously, your machine is very loud. Can you compare those numbers with current generators in the market? What were you use?
I have not. I would assume it's a little higher. Obviously, yeah, it's definitely higher. What we did on our decibel rating, that was for the operator. We measured them immediately by the turbine. But as soon as you started walking away and you were 30, 40 feet away, it significantly dropped off to below the OSHA recommendation for ear protection. So pretty much, if you're not the operator, it's not significantly louder than traditional engines.
And if we were to turn this into like a turbo, like a gas turbine, we would connect it to a shaft and enclose it, and it should bring down the volume as well.
They're making the ultimate mistake. People are looking at the tail number and they're talking. Look at the crowd.
Yeah.
Make sure you guys speak up, man. Up there it sounds like out of a can, you know. Yeah, we'll do our best. You guys should shoot this damn thing and of course back to the wall.
Oh, that's
One professor over there pretty confident.
That was, oh, sorry. Dr. Wilkes.
You can just show us, and once in the end they can come and look at it.
Yeah, just do that instead of passing it around. I'm going to make sure the video works.
What about the other one? There's the other spool, the little piece.
It's on the thing.
It's on there. It's on the thing. Spool. The first like material that we got.
Oh.
Is that what you use?
No, that's the good stuff we have. No. No, just start the video. Where's the present button? Where's the present button at?
That right there. You get it?
Okay, so it's just gonna do that then. I guess that'll be alright. When we click on it. Alright, everybody know what they're doing?
Yeah, I'm just like reading. Do you have your slides like memorized or not? Okay.
Stand back here. I'm gonna be the one on here.
Okay. I'll tap it.
Just at the end, just talk.
How much is like supposed to film it cost $24 per company? The bulk calls cost over 80% less than human. What does bulk calls cost?
80% of fucking that.
So like it's average $30.
Say like
$5 a kilogram.
Yeah, you could say roughly $5 a kilogram. Is that right?
80% of 30. Or 20% of 30.
That was amazing presentation. That was really good.
Really?
Thank you.
I didn't think it was that good.
It was very good. You had no questions. You explained. You left no questions on the table, basically. It was pretty damn good.
We got stuff.
Yeah, we got stuff. We got prints. You'll see the pictures. They look a lot better.
Yo, so how long did it take you to do your slides? You had fucking time.
Pretty. Huh?
Yeah. How long?
Oh, yeah.
Yeah, anytime. No.
I'm just gonna look at the time when we start.
We did it with like 2.5, 3 minutes for you. That's how much, when we did our practice.
That's what you guestimated it?
No, we timed us and then we just skipped through your slides.
You
Oh, so that's how much you left for me?
Yeah.
Oh, that's perfect.
Yeah.
I'll get it done in a minute and a half. This is our purpose. Thanks a lot. He said you left me 2.5, 3 minutes.
Yeah, you should be good. If it's under that, it's okay. But I read yours, and I just read it right off the slide. And I heard the comments.
You think I should just read it right now?
No. But like, if you have to, it's okay.
But it's hot in here.
I'm not taking this jacket off.
No, it's,
It's
I'm hungry too. I'm
an hour from now. I'm gonna
so
go
is there full presentation?
There's stuff out there. I'm gonna go grab a drink real quick.
It's all this in the seniors, and then after that, it's gonna be all the first semester presentations. I think there's 2 of them.
Put do not disturb on when you get calls. So I put do not disturb on. Yeah, that's it. That screams of dad's 100%. I'll tell you what, I am. Up on my house. Dude, it usually takes me 52 minutes to get here. Guess how long it's taking me to get here? 30 minutes. I mean, I had hunting boots on when I got here. Oh my god.
Dude, I'm just like when I said, I was like, this is all I have.
I mean, with the mullet, what do they expect?
I was gonna shave the beard and the mustache. I was like, I can't really
You guys are lucky that the our friend isn't here this time.
Oh yeah,
that douchebag.
That guy.
Who? That's
the
not.
guy that was like, why don't I just get an Apple Watch?
Is that Dr. Whitman?
I thought that was his friend. I guess it was.
Is it the guy with the
Oh, is it Taylor?
Is it the guy with the purple shirt on?
Who is it?
No, was it?
No, not Dr. Taylor.
The guy right there, Stan,
with the purple
shirt on.
Yeah, that's what happened.
Oh yeah, I don't know who he is, but he always asks hard questions.
I know it was a hard question.
Yeah,
I don't think he works here.
No, he does.
He does.
He's just like in charge of stuff.
Literally the first
Oh, he's like the pros.
I think he's EE.
No, I think he's
No,
like.
I think he's like the provost or whatever
Yeah.
the fuck it's called.
One kid was told.
Yeah, like the.
Oh, I know.
Dude, I was the only
He's in a group with me for the one project I have.
He was cooking.
I couldn't even understand him.
That might be me.
It's gonna be like.
Told their shit's obsolete.
Huh?
Told their shit's obsolete. The first group. You basically told them they wasted their time.
Yeah.
It's crazy. The first group.
Oh, the Apple Watch.
No.
I didn't see the first
They
one.
were like, they used a PLC for something, and he was like, you couldn't use a microprocessor. And they were like, oh, we didn't. He was like, doesn't make sense. He just kept like, they kept trying to answer anything.
He's like that. He'll like argue.
He's like the first. Basically said the wheelchair thing.
The wheelchair ones. Quantum.
He basically said like your whole point is to avoid obsolescence, but you're obsolete in certain parts.
Damn.
Yeah, he basically told them they wasted their time. It was fucked. John, go back.
industry standard is about a 5% tolerance. The industry standard is about 5% tolerance.
Say we would like to get it below.
Okay, so don't say it's an industry standard.
No, I don't know what the industry standard is. We still have 5 minutes, but we're coming close. Just look up tolerance on PLA film. It says it on the spools, but we didn't have a spool. What names? Our names? The order they're in.
So am I right after that?
This is the order we're saying our names, guys. Me, Jack, Alexis, Stone. 0.5 millimeters. Yeah, that's
plus or minus. Plus or minus.
That's like 0.5% tolerance.
No, it would be. It's 5 over 1.75. 0.05.
0.5 over 1.75.
0.5. It's like 3%.
No, it's 0.3%.
No, that's times it by 100.
Times it by 100.
Times 100. 28. That's wrong.
Yeah, it's wrong. It's 0.3%. I'm pretty sure.
No, it's
the 0.5 divided by 1.75. Is it 0.5 actually, or not like 0.05?
0.5 millimeters. So it's 0.005.
Wait, Amazon Basic small point has a.
It's point. Oh yeah, but that's
any given point the stroke is could be as large as 1.8. Oh, it's 0.05.
Yeah, it's 0.05.
So 0.05.
It's gonna be 3%, like 2 point something. Yeah. Times it by 100.
It's 3%.
You could say that if you want. Just say the industry standard is 3%, but we would like to get below 5%.
Okay.
That's our future goals.
Or even close to 3%.
Yeah.
Fuck, so I'm gonna fuck this with whatever.
Where'd you get that? Oh, you can't button the bottom button, I see.
I could.
No.
Maybe insecure.
You fucked me up.
Do you want me to see this?
I got it.
He's got it. Stand over here. Do you want to stand over here? I'll move over.
You guys switch spots.
I'll move over. I'm gonna move over.
Yeah. When he's done talking, you come over and switch with him. And you go stand over there next to the machine. Should be like, good morning, everybody.
Yeah, we can say that.
It's today the 29th.
Okay, everybody, so we're on to our next block. We have 3 teams coming up, and then our lunch. So up next is FilaMax.
Right. Morning, everybody. Our project is FilaMax, and our slogan is maximizing 3D printing. I'm Josh Hamilton.
And I'm Stone Warmouth.
Our advisor is Dr. Moo.
So the background of our project. So additive manufacturing, better known as 3D printing, is a rapidly growing industry. Printers as well as filament could be very expensive. Both the filament and printers, they can be very costly to the user. And even though 3D printing filament is very abundant, it's easy to get, it is very costly to the user when you're printing multiple parts per day, per week. It could be very costly. So the much cheaper option instead of 3D filament would be purchasing bulk pellets and then converting it into filament, as you can see what our project was. However, these pellets cannot directly be used to make 3D printed parts. They have to be converted into a filament. The purpose of our project, as I just talked about, is research, plan, design, create a PLA plastic filament extruder for the Wilkes University Additive Manufacturing Lab. This would allow the use of bulk PLA pellets, as shown up here, to be used to make new filament. The main purpose of this project is to save money. It's going to save Wilkes University tons of money, hopefully, because the typical cost of a 3D filament is between $20 and $40 per kilogram, and bulk PLA pellets are roughly around $6 per kilogram. which is about 80% less than the pre-made filament.
As for our research, on the left here we have a schematic of generally what we try to accomplish. As you can see, we had a motor driving a auger bit, which will house PLA pellets, and in that auger bit, they will be heated up and then extruded through a nozzle, and then cooled by fans we will provide. On the right here are some of the competitors, and as you can see, most of them go for a horizontal design. We hope to we accomplished a vertical design, which uses gravity to help us accomplish our goal easier.
That's for our design. On your left are the basic inner parts that compose our machine, which includes at the top the funnel, which goes into our auger housing. Inside the auger housing, we have our auger screw that is being driven by a motor. And then around the auger housing, we have 3 heating bands that help heat the PLA material down, and at the bottom, they'll extrude. On your right is the framing around our machine, and then in the middle, it's our basically finished model, where in front we have the electrical components that compose our model, which include 3 PID controllers, 1 speed controller, and some emergency buttons. And then you also have one access point at the top where you can pour in the PLA material, the PLA pellets, and then you have this door at the bottom where once the spooling is done, you can feed the spool out. So ordering and finding parts, we insource a lot of parts in-house, and Mitch helped us a lot in designing and manufacturing some parts. Some of the parts that we sourced in-house was the funnel and the winch motor, and then other parts that Mitch helped us manufacture were the outer housing and the nozzle tip. And then one of the most important parts that we ordered online were the auger bits, the speed controllers, and the PID controllers, and the rest of the stuff were mainly add-ons, so our project could work a lot better. So this year are pictures of the start of the assembly fabrication. On your left, you can see Josh working on the funnel, grinding it down. On the middle, it's me, early stages, working on the frame. And in this picture, we were actually testing a smaller motor being driven by a screw that's inside the outer housing to see if it fits and if it doesn't grind on the outer housing on the inside. And then on the far right, on the right, you can see the nozzle tip that Mitch helped us manufacture. And then here are our electrical components. We have the electrical box that was also manufactured in-house. And then here at the top is where you're going to see all of our electrical components in there. We have 3 heat sinks, and then our power source, and then the wiring. And then on your right, you have 3 heating bands around our auger housing that are covered around with insulation. And then this is our finished machine. As you can see, it looks pretty similar to the design that we wanted, and as of now, it functions really well.
As for some challenges we faced, our first one was the lack of torque. So our first motor on the left here was a windshield wiper motor with roughly 20 to 30 newton meters of torque. We found this to be insufficient in turning our auger bit because of possibly friction throughout the auger housing and also misalignment. There was poor alignment there. So you can see we improved with a 1-ton winch motor, and we also improved by cutting the tip of the auger bit in order to get a better fit for that pump. So the the second was heating. We originally started with one heating band, which we found out not to be getting a consistent melt through our entire housing. So we improved to 3 heating bands, and this allowed us to get a much more even melt throughout the entire auger housing, as well as a much more consistent temperature. Our third challenge was the coupler, as I touched on. Originally we had a flexible aluminum coupler, as well as a port connection between this coupler and the auger shaft, as you can see on the left. About 2 minutes after this picture was taken, the coupler actually exploded because of the misalignment. So we then had to upgrade to our new flexible steel coupler with a much better connection between shaft and coupler.
Once we completed the design of our machine, we began testing. The first test we completed was the melt test. We wanted to see if the pellets would get a complete melt in our chamber. Our initial desired range of temperature was between 300 and 325 degrees Fahrenheit. From our testing, we found that around 350 to 400 degrees was the ideal range for our machine. Here I have a small video of the first test we did just to see if our pellets would melt. You can see we were very early on in the stage of development. The plastic, you can see, is not fully melted. It's still pretty thick. And this helped us determine our range of temperature. The second test we did, we installed the nozzle, and the nozzle has a 0.07 inch hole in it, which is roughly 1.77 millimeters. We still had our single heater on and our wiper motor. And our first run, we used 2 different filters and no filter. Our first run, we used a small copper filter, and we yielded a 0.059 inch filament. Our second run, we changed the filter to a larger steel filter, and that yielded a 0.055 inch filament. And the third run, we removed the filter and got a 0.05 inch filament. We decided in this test that no filter would be the best because it yielded the most consistent filament and used the least amount of torque on our motor. Our third test, we upgraded the motor to the new 1-ton winch motor, like we spoke about. And our first run, we got 0.03 inch filament, and our second one, we got 0.035 inch filament. This test, we found that we got a very, very consistent filament, but it was too small for our desired range. So our fourth test, we made a new nozzle size and enlarged it to 0.1 inches, which is about 2.54 millimeters. And in this test, we had our winch motor combined with our 3 heaters. Our target diameter was 0.07 inches, and our first run, we got 0.065 inches, as you can see in the picture and the spool up on the table here. Our second run, we got a little larger of 0.075 inches, and our third run, we got 0.068 inches. We achieved about a 7% tolerance with our filament. And our final test, proving that our filament is usable, we used it in a printer in the additive manufacturing lab, and we printed 2 small items. We printed a small pinky ring, as you can see in the top picture, and a Wilkes logo keychain, as you can see in the bottom picture. This proves that our product is suitable for use on 3D printers.
So first, some further improvements for our project. So the first one would be the spooling mechanism, as we can kind of see up here. We actually took this design from Thingiverse. So someone actually designed this prior to use on the 3D filament extruder. And what it does is it will actually spool the filament on the spool, and it moves it back and forth so it doesn't get bunched up in one area. We would like to actually place this in the bottom of our product, so when you get the extruded filament in the machine, you can attach to the spooling mechanism, and it will spool it for you. It will be driven by a motor as well, and you can take out a fresh spool of filament. And the accuracy of our filament. Like Josh said, we achieved around like a 7% tolerance for our filament. And the industry standard is about like a 3% tolerance for filament, if you take a look at it. But we would like to, reduce our tolerance down to like 5%, even closer to 3%, just to get a more accurate piece of filament that would be, you know, that would produce better quality products within a 3D printer. And we would also like to improve the purity of our filament and just kind of reduce, you know, air pockets within and make our product more consistent.
We'd like to welcome anybody down to the stage during the questions section. We have a little setup of our process. It starts with the PLA pellets like we talked about, and just the process that we went through this entire last semester. And we'd like to make some acknowledgments. We'd like to thank Dr. Moot, our advisor. A huge thanks to Mitch Adams for help with designing almost this entire project, Dr. Bednars and Dr. Zhu, and every other professor that helped us along the way, teaching us the knowledge of how to complete a project like this. Any questions? Yeah, it's supposed to be run. We didn't change much. It was just the motor is hard to control sometimes. There's clogs in there. It's not super consistent, so we have to adjust the speed that the motor goes. You have to adjust it by looking at the filament coming out. Sometimes it would slow down, so you'd have to speed it up. So there's just inconsistencies in the usage of the machine.
So in order to get to the tolerance that you're driving for, which is less than 5%, then you're going to try to optimize the design. Yeah. In other words, the speed of the motor and a variety of other things to get to that point, correct?
Correct.
Okay. That's what I wanted to know. Thank you.
And another thing that we also try to, we're going to try to optimize is the cooling of the filament when it comes out. Because sometimes it sticks together, so that's another thing we're trying to improve.
Yeah, sometimes it's too hot and it stretches slightly, so that will cause inconsistencies in the diameter also.
When you're in that spooling process, you have to maintain a constant.
Yeah, the speed of the motor has to relate to the speed of the spooling. Yeah. They have to be the same, or else it could.
There should be some synchronization between those two.
Yes.
Okay.
So the system is powered by both AC?
The heaters and PIDs are controlled by AC.
The overall system is plugged into the wall?
Yes.
Yes.
Yep.
Okay. So what kind of motor do you have there? The winch motor, what kind of motor is that?
It's a small, it's a 1-ton winch motor and uses a gear reduction to achieve that. It's a small.
It's a gear ratio. So it's an AC motor?
Yes, it's an AC motor.
It's an AC motor with a gearbox inside?
Yep.
What's the gear ratio roughly?
I don't believe we looked into it. It just
But
would
it
you.
generates 1 ton of force?
Yes, 1 ton, or no, 1 ton of force, and I believe it was 9,000 Newton meters of torque, which is, it's much more than we require for this.
And as I've seen, the vehicle provided sufficient torque to drive the system?
Oh yeah, yes, very. Like Jack said, we originally had an aluminum coupler on it, and it tore that apart very quickly. So we had to upgrade to much bulkier components once we use that motor.
Are you doing any cooling before spooling?
We don't have that installed right now. That's what we'd like. That's one of our future improvements, along with the spooling mechanism. So when it starts to spool, it would cool it down faster. We have all the components for it, but we wanted to get filament that was usable before we could install.
So right now, like a flow, only a few seconds, it doesn't seem to be sufficient.
No.
No, it's too hot still.
Yes, it's very hot.
Yeah, right now we have 5 fans that we can put in a single bracket around the nozzle that can help cool down a little further. Or we have the other option of...
And you just put a fan there, would that be sufficient?
I think we'll need more than a fan. We also have the option of using compressed air. The additive manufacturing lab has an air supply. That's our other option that we could use. But 1 fan probably won't be enough, so we have multiple fans that surround the entire thing.
Final question. What about ventilation? Because this could be some harmful, you see what I mean? Is there anything we do have? But that has to go somewhere outside, not just indoor. You see what I mean?
We haven't hooked it up to an external exhaust yet, but when we were testing, we had it above duct above it, so if there was any harmful gas, it would get sucked outside. That, in our initial testing, came hooked it up to any specific dock score or anything like that.
How did you define tolerance again?
We just measured the filament. I think it was.
How is it defined?
The tolerance is the diameter. We wanted to get 0.07. That's industry standard, and we compared our results to that standard.
How consistent are those measures, but not 3.068? One measurement?
It was very consistent. Like this entire spool, we were measuring it while we were spooling it. This is the 0.065. It was slightly smaller, and it was very consistent almost this entire length of that thickness.
Thank you very much.
Good luck, guys.
Should I load no videos, Nick? No video? With video? Okay. Yeah. We just wanted to back up in case, but okay, thank you. Good spot? Yep. Screwdriver?
Good morning, everyone. My name is Wilkes Engineering. I'm Andrew Wearable. I'm Nicholas Engineer. And this is the Overcast bait launching system. So, today, we're going to take you through the lifetime of our project, including why we chose to undertake it in the first place. We're going to talk about our design, our testing, fabrication, refabrication based on things that went wrong. We're also going to talk about some managerial paperwork and future opportunities for it.
All right, so the problem we're trying to solve is related to surf fishing, more specifically the limitations of hand casting. The geography of most beaches create turbulent waters and wave formations that form anywhere from 100 to 200 yards offshore. And the goal of the fishermen is to cast to or beyond these distances. However, even an experienced fisherman is going to have trouble casting beyond 100 yards. This video here shows that exact problem. To solve this problem, we designed and fabricated a pneumatic bait launching system that alleviates the need for hand casting. This system features actuators, controllable launch distance, and numerous safety features.
So as Nick said, we have a controllable launch distance that's achieved via our computer control system. Next up, we have easy portability so that you can use it on the beach. We have our 200-yard maximum launch distance that we're trying to reach for. As Nick also mentioned, we have numerous safety features to guarantee the safety of the user as they're using the product. And the fifth, in our deliverables, we have an operations manual for the user. So up next are some key changes from last semester to this semester. First off, last semester we planned to use the solenoid valve to actuate the launch. This semester that's been replaced with the ball valve. Next up, last semester we planned to have a computer actuated launch sequence. This semester that's been replaced by a user actuated launch sequence with a computer controlled safety. Last semester we planned to reach 300-yard maximum distance. Due to hardware limitations, that's been adjusted to a 200-yard maximum launch distance this semester. And then finally, we originally had a linear dropout voltage regulator for planned for last semester. That's been replaced with a buck converter voltage regulator this semester.
So, as for a few specifications, like you mentioned, we changed the LDO regulator to a buck converter. Since this is intended for mobile operation, we need a robust power supply so it doesn't die in the middle of a fishing trip. This circuit achieves the same function while consuming a lot less power. Next, we need a screen that is bright enough to see while you're at the beach on a bright day, so we chose one that had at least 1,000 lumens, which is sufficient for that purpose. Last but not least, we need an analog to digital converter with a resolution high enough to detect small changes in pressure in the cylinder for the feedback.
On the mechanical side, we chose to have high safety factors for all of our structural and pressure bearing components so that nothing fails during operation. For operator safety, we've installed a 175 psi manual or automatic pressure release valve. All the components on the assembly were designed with corrosion resistant materials, whether that be aluminum, stainless steel, or plastic, so we don't run into any corrosion issues with the salt air at the beach. And then finally, our barrel has 25 degrees of adjustment in angle so that you can adjust the trajectory of the projectile as it leaves the barrel.
So, right here is a Gantt chart breakdown of our schedule. Last semester we were focused on the design portion. This semester we were focused on fabrication, testing, revision. Right here is a breakdown of our expenses. Last semester we were over the provided $500 budget, but thanks to a generous donation from Pennsylvania Steel Company and support from Dr. Galusin, we were able to bring this down to $434, so we're now under budget. This is our work breakdown structure. This shows how we partition the work necessary to complete the project to the timelines assigned in the schedule we just saw.
So the fabrication process began at the beginning of this semester with our initial prototype constructed by March 3rd. As you can see from the image on the right, that this prototype does not include the screen or the battery box. However, we did not deem it immediately necessary for our initial launch testing. The projectile mold was 3D printed using TPU. Each mold is capable of creating a single 5.5-inch long projectile with a 1.93-inch diameter. Inside the projectile is the weight, bait, the hook, and the fishing line, all frozen in ice. These molds are made out of TPU as it is flexible in nature and will not crack as the ice expands. Lastly, we apply a liquid waterproof rubber sealant on the inside to create a watertight seal.
So up next we have a couple comparisons between our CAD models and our actual assemblies. Up to my right is the screen and the electronics housings shown in CAD. And then to my left is an actual picture of what that looks like today. Next up is a picture of the full assembly. So again, to my right is our CAD representations of that assembly. And then to my left is the actual assembly as it is here.
Here is the abstract and physical realization of the control unit. This screen board right here is the Raspberry Pi. That is the computer which takes the user and sensor input data and makes decisions regarding what it sees. All the way on the right here, we have our PCB, which houses the control circuitry. So that is how the computer interfaces with the circuitry required to energize the solenoids and take the input data. In the middle, we have that 12-volt to 5-volt buck converter, which takes the battery supply and puts it to a safe level for the computer. And all the way up in the corner here, we have our inertial movement unit, which displays a real-time angle of the barrel on the touchscreen at all times.
So up next is testing. So in order to test, what we did is we first tested each constituent subassembly first. We started with the pressure bearing components to ensure that there were no leaks or sealing issues. Then we moved on to the electronic components to make sure that they all operated together properly. Having tested each of those subassemblies, we then comprised the main assembly and tested that in 3 main phases of distance testing. The first run was done with a solenoid valve. After having learned some things from that first test run, we then made improvements and switched to the ball valve. Having verified the performance of the overall device with the ball valve, we were then ready to move to beach testing using actual fishing equipment.
So the pressurization process came with numerous setbacks. We attempted to achieve a pressure of 150 psi without any leaks. Our initial fabrication, we were only able to achieve 30 psi using thread tape, and we used 2 different types of leak blockers to attempt to fix this. The first had no effect, and the second one got us to about 80 psi. After investigating, we found that the threads inside of the pressure vessel were being heavily damaged by the repeated threading and rethreading of our steel pipes. So to fix this, we fabricated a coupler, male and female threads, that replaced this. So the images on the right represent the old and the new threads. With those new threads, thread tape, and a hard sealing leak blocker, we were able to achieve a pressure of 150 psi for 2 launches, and we have not had any leaks since.
To know how much pressure is in the cylinder at all times so the user is aware, we use a 5-volt, 200 psi linear pressure transducer. So this sends an output voltage that is proportional to the amount of pressure built up. So we measure the output voltage compared to a known pressure source, and as you can see from the figure, it is a very linear trend, which simplifies the calculations that the board needs to do to display that real-time pressure.
However, the output voltage of the transducer is higher than the board can handle, so this needed to be shifted down to a level that was safe so it wouldn't kill the control system. This was done from a very simple voltage divider circuit shown right here, and this is the equation that is in the computer that takes that voltage and converts it to a pressure.
So the first step of our launch testing was to experimentally determine the ideal angle to get maximum distance. We found that at lower pressures ranging from 0 to 70 psi, our ideal launch angle ranged from 41 to 43 degrees. As we increased the pressure above 70 psi, this ideal angle dropped down to 38 degrees. The reason for this is because the increased drag force is non-linearly proportional to the increase in velocity. Therefore, greater horizontal velocity is required to overcome. Now, the next step was to test the relationship between pressure and launch distance. The solenoid valve actuated a launch of a 0.9-pound projectile, and the blue dots represent the average of multiple launches to 10 psi increments ranging from 50 psi to 130 psi. After we switched the solenoid valve to a ball valve, we found an 80% average increase in distance represented by the red dots, with the largest launch distance being 218 yards.
So to utilize the new ball valve, what we had to do was design a mechanism that would open quickly. So to do this, we installed a lever on the side of the ball valve. This attaches to a high tension spring going down. In order to use this, the operator will take a charging handle, cock this valve lever into place, which will hitch on the tooth of this trigger latch. When the user is ready to fire, what they'll do is use the control system to release the solenoid safety pin up there. They will then pull a draw cord, pulling that trigger latch backwards, releasing the valve lever, and the spring will snap it open very quickly to give us the push that we need to fire the projectile. So moving on to distance testing with our ball valve, this was done with 3 test projectiles. These were constructed of a thick-walled PVC tubing that was turned on a lathe into the shape that you see here. We pressed in an aluminum core. These test projectiles came in 3 weights, 0.9 pounds, 1 pound, and 1.1 pounds, and that was to simulate the variation in rigs that fishermen might use. So we then tested each of those projectile weights with 2 launches in increments of 10 psi, from 60 psi to 110 psi. What we observed from the data we collected was that from about 60 to 100 psi, we saw a fairly linear relationship between pressure and distance. We got proportional distance returns, but then after 100 psi, it started to plateau. And we hypothesized this was because the compressed gas, or we reached the maximum allowable flow rate from our fittings.
So the data from the 0.9-pound projectile was used to model the equation shown on the screen. This equation takes the user data, the user's distance, and outputs the required pressure to achieve that distance. To derive this equation, we fit a curve to the data, which provides an accurate prediction within the range of 100 to 200 yards. It is important to note that the weight is not included in this equation, as we did not have sufficient data to accurately determine a variable which represents the effective weight on our launch distance.
Now, of course, since we proposed this project last September, our overarching goal would be to go to the beach and use it to catch fish. So that's exactly what we did over Easter break. Our first day of testing did not go as we hoped because our projectile molds produced a projectile that was very hard to remove, and it also broke when we were successful in removing it, which is not good for a launch. This caused us to switch to TPU projectiles, which we saw earlier, or right here. So, our second day of testing went much better. We were able to catch 2 dogfish sharks. One is pictured here. Maybe it's because the second day was an overcast day and the first day was sunny. Who knows? Maybe it's a good omen. So, what you're seeing on the screen right here is a representation of what they are looking at on the cylinder. As he keeps pumping, you see the pressure increases because it is a real-time readout. Whenever the user is ready to actuate a launch, all they do is hit the release safety button that pulls the pin up, and he pulls the cord, and you get a launch. It is that simple.
So, having seen what the Overcast can do, we'd like to see what it can do in the future. And our first step to do that is to increase the diameter of our ball valve and our transfer pipes to increase our flow rate. More flow rate means more push means more distance, and more distance means bigger fish. So, we'd also like to reduce our system weight to make it a little bit more portable and user-friendly. And then very importantly, we'd like to improve our mathematical model used for our pressure and distance calculations. In order to do that, we have to collect a lot more data.
As for the circuitry improvements, we'd like to turn all those individual PCB boards that we saw previously into one unit that is dedicated for the whole operation, including the microprocessor, the voltage regulator, and all the control circuitry. We would also like to consolidate the screen, the battery, and that circuitry into one box, so we only need interfacing wires between separate systems, plus wire grouping that we can do. And we would also like to turn the Python script file that runs the software into an executable, so that way it runs a lot more smoothly in the future.
We'd also like to add some other possible additional features. These are mainly ergonomic improvements, and these are listed on my left up on the screen.
Now, it goes without saying, but of course we would like to thank all the professors for teaching the courses in the past 3.5 years that gave us the ability to be able to design, fabricate, and troubleshoot such a product. We'd also like to thank our advisors, Dr. Gamari, Dr. Anaya, and Professor Taylor.
We'd also like to give a very special thanks to Mr. Rich Adams, the university's machinist, who helped us throughout the entire process. His assistance, advice, and work have been truly invaluable throughout the process of making this project. We truly could not have done it without. We'd also like to give a special thanks to Pennsylvania Steel Company for their generous donation of the aluminum tubing that has become the Overcast Wearable.
Does anyone have any questions?
So one of your main design choices was to prevent corrosion, so you used aluminum and stainless steel. But in contact, they will corrode together. So did you make sure that the aluminum and stainless steel are in contact?
We have the only buffer between them right now is thread gauge, and other than that, we do not have any.
So over the years, there were many projects like this. You guys were the best I've seen. Very impressive. It's really, so who came up with the idea of just using a manual pump to create the pressure?
We kind of collectively
That was,
decided.
in my opinion, that was the best idea of this project. Because the power system, usually that's what get people, you see what I mean? But that seems to be a very intuitive idea, but many times great ideas are simple ideas. So this, I really, that's very impressive. So.
You can measure that you see an advantage of using the metaphor
Yes, in the future, if we were to take this to large-scale production, we wouldn't stick with the Raspberry Pi. We'd have a dedicated microprocessor designed specifically for this system.
What if you change the control to other kinds of like mechanical or other physical components tied to the system?
So if we use that microprocessor, then we would have that dedicated PCB board that I talked about that would house all of the circuitry rather than all those independent circuits in the box. That would make it a lot smaller, so it would reduce the size of the electrical hardware required to perform the task that it does now.
So in that instance, then, by switching over to the dedicated microprocessor board, would you stick with Python, or would you move to something like C# or C++?
Definitely move to something like C# or C++. It's much more robust, and that's pretty much the industry standard.
C# would be it's a lot better programming language, and you'd have a lot better, you wouldn't have all the memory leaks that you're going to get with Python.
Yeah.
Have you considered using the scuba tank as an alternate source of air pressure?
So at the beginning, we did consider having compressed air tanks for the pressure, but we realized that if you were going out to the beach, you'd have to lug this thing out there and all your equipment. You'd also have to go back and take a very heavy compressed air cylinder out there too.
But if you really did want to use a compressed air tank and take it out with you, we do have the regulated solenoid filling valve here. So all you would have to do is plug it in. You would input your pressure to the control system, and then it would automatically shut off when the pressure cylinder reaches your desired pressure.
If you start to use it on fishing boats a lot, that might be something to rethink, because scuba tanks and fishing sometimes go hand in hand on the same vessel.
Okay.
You have another minute left. Are there any videos you wanted to show that you didn't get a chance to show?
Sure.
Yeah, I'll do the last one.
They have a 500 megabyte file, so they got something in there.
only have 70 slides.
So this was done on the Greenway, and that shows that the line is very compatible with it. Here's our beach testing where we launch, and it's very hard to see out there, but it was in the air for over 5 seconds. So it lands, and that's where we caught the fish. This is a slow motion video where you can see the projectile coming out, and there's the fish. That's our bait. And this is one of the dogfish sharks that we've got.
It's already plugged in. All you have to do is hit this to go forward, this to go back. And there's a laser pointer up top if you want. That's Dr. Anais. That's not mine. That's up here.
All right, good morning, everybody. We are the Mitsubishi No Melt team. My name is Connor Gorman.
I'm Cora Shine.
I'm Nathan Van Fleet, and our project advisor is Dr. Rizal. We'd like to begin by stating that our project is a little bit different than the other projects here today because we're focusing more on research and design than we are designing buildings.
All right, so just a general outline of our presentation here. To begin, we'll go into a little bit of a recap on our problem, the theory behind it, and our hypothesis. We'll then move on to research tests and testing conducted this semester, materials testing, dielectric permittivity testing, and radar testing. And we'll end with our testing apparatus design for Mitsubishi's extrusion line. So we worked with Mitsubishi Chemical on the non-destructive method of testing for no-melt defects within their polyethylene slabs. So when no-melt is detected, the pressure and temperature parameters can be adjusted online to eliminate the defects. And right now, light translucence testing is used to test their natural non-colored slabs, and slit tests are performed on colored slabs. So as you can see in detail on the right, translucence tests show a thin opaque band when no melt is present, and no melt shows as a lighter band of material in the colored slabs. So going into our hypothesis is that no melt, being improperly melted polyethylene, has a different crystalline structure and therefore different material properties than non-defective polyethylene. This is due to the inconsistent melt properties of polyethylene due to its high viscosity and high molecular weight. All right, so the material testing that we sent out for consists of X-ray diffraction testing as well as differential calorimetry testing. X-ray diffraction testing consists of bouncing X-ray beams off of the polyethylene sample to analyze its diffraction patterns. And the intensity of these diffraction patterns, as shown on the y-axis, determines the structure and electron density of the crystalline structures of the sample. So the key takeaway from this data that we see is that the small differences in the height and breadth of these intensity peaks indicates a difference in crystalline size between the healthy and the defective samples. Moving on to differential calorimetry testing. This consists of measuring heat flow into or out of the sample as a function of temperature and time. As you can see, the healthy peak melt temperature is 136 degrees Celsius, which is within the typical range of high molecular weight polyethylenes. However, there is a second peak melt temperature of 144 degrees Celsius, which indicates that the no-melt defect may have different thermal properties than a healthy sample. One caveat that we had to this testing is that the samples we sent for testing did contain an additive that may have contributed to this behavior. So more testing with more no-melt samples would be needed to solidify our hypothesis. But we were able to go and build upon this to test for differences in material properties due to the changes in crystalline structure between the defect and non-defected slabs.
So our theory was that the no-melt defect had a different crystalline structure than the normal polyethylene, which would affect its material properties, one of which being the relative permittivity. Relative permittivity is the factor by which a material affects an electric field between two charges compared to that same field in a vacuum. So in theory, we would be able to send electromagnetic waves to a sample of the defect, measure the returning signal, compare the strength of that signal to the returning signal from a healthy sample, and there would be a measurable difference between the two. So to test that theory, with the help of Dr. Sabuni, we used a relative permittivity probe connected to a network analyzer to send electromagnetic waves into a sample and measure the reflected signal. This was done over a frequency range of 1 to 20 gigahertz. The results of this test showed that there was roughly a 50% difference between the permittivity of the defect and of the healthy sample. There were some limitations to this kind of test. The probe only had a max penetration depth of 2 millimeters, so it couldn't detect the defect on the top and bottom of the sample, only from the cut side that showed the cross-section, which wouldn't be available if we're doing non-destructive testing. So we moved on to a type of test that would be more viable on a production line, which was the microwave radar testing. So from Mitsubishi, we received 2 large samples of the polyethylene slabs. Each sample contained areas of healthy polyethylene and areas of defect. From each of the large samples, we took 2 smaller sample sets. Each set contained a healthy piece and a defect piece that were the same size. So for the test, the samples would be placed in a metal cylinder surrounded by 4 Vivaldi antennae that could both send and receive microwave signals. And they could do this over a range of 1 to 10 gigahertz. On the left up here is a Vivaldi antenna and the field pattern that it produces. We use these antennae because they're directional and they have high bandwidth. And then on the right is just an example of the type of graph we can generate using the data from these tests. This one just shows the range of frequencies. So the first 2 sets of samples were tested using all 16 different configurations of sending and receiving antenna. The second set were only tested using through transmission and reflection, which are the 2 examples up there. This is because the other configurations wouldn't be able to be recreated on the production line. So during the test, the samples were placed in the center and microwave signals were transmitted to them, where the electrical properties of the sample interfered with the signal. The properties were mostly the conductivity and permittivity of it. The signal was then received by either a different antenna or the same one that transmitted, depending on the configuration we were using. Then we would get the results from the network analyzer that was attached to the core antenna. The results were in the form of scattering parameters, also known as S parameters. They're the ratio of the power of the received signal to the power of the transmitting signal. They're measured in decibels and they're logarithmic. All the antennae are numbered, and the 2 subscripts of that parameter refer to the position of the receiving and transmitting antenna, respectively. And so from this test, in the results, we were looking for a significant change in the S parameter coefficient between the healthy and defect sample when they were measured at the same frequency, which would then indicate that there was a difference in their electrical properties.
The next 4 highlight those with the blue boxes, that way you can see it better. On the next slide, we have the second 3D high-bar sample data. You may be questioning, why is it not consistent with that approach? That's because with the no melt defect, the structural variation does not allow for consistency in frequency sensitivity. So we're not expecting it to have the same kind of pattern to it. We're just expecting that we can consistently detect that peak difference between the healthy and the defective samples. Next, we have the first sample for the black high-bar samples that we tested. Again, we have the same graph on the left, dictating the entire frequency range, and then on the right, we isolated the peak frequencies around 9 to 10 gigahertz. Here we have the second sample set for the black high-bar sample. Again, as you can see, right around 7.4 gigahertz, we have that massive peak difference. That's what we're looking for in our testing results. Now, after doing that data analysis, we have to refine our testing requirements for our design to make microwave radar testing apparatus. Mitsubishi's requirements were that, firstly, we have to be able to scan the entire slab width to detect if there's any defect present. Secondly, we also need to design a device that can withstand the weight of the slab going over it. The slabs can range from anywhere being 150 pounds all the way up to 200 pounds. So there is a big weight consideration there. Additionally, from our testing, we determined that we need to have shielding to go around the microwave radar. That way, there's no signal noise from the manufacturing floor that will interfere with our measurements. Additionally, with using microwave radar, we need to have a network analyzer. Unfortunately, this will jack the price of our design build a lot because of how expensive the network analyzer is. And that high cost is also derived from the fact that we're trying to replicate our testing. We're testing the frequency range of 1 to 10 gigahertz.
So here is a 3D render of what could be a preliminary design of what our testing apparatus could look like. The main part of it is going to be made out of steel, and with the thought in mind that we have to withhold the weight of the slab going across it. Now that antenna configuration in the middle will be sliding along that rail manually at different intervals in order to periodically go through that range in order to test the width of the slab. So again, the frame, what they wanted us to do was make this testing apparatus available to go and be implemented on their line that already exists. So there's black caps on the ends of the steel beams, and that is just a representation of the table that they want us to fit it into. The frame itself is made mostly out of solid steel bars, except for the crossbar, which is a steel tube. And then we have a Teflon on top of that steel tube in order for its low friction coefficient when the antenna slides across it. We did an FEA analysis of it just to see how it would stand up under pressure and detect any critical points of possible failure under weight. That we had determined that the possible critical points are a lot on the joints and on the L brackets. And there was a small displacement of a 0.2 inch on the middle of the crossbar under the 30 psi pressure that we put on. This is the model of our antenna for the that would slide across that Teflon rail. The shielding was taken off the top of it for the purpose of just seeing the antenna and on itself. But normally there would be shielding on the top of it. There's a bracket in the back for the network analyzer to slot into in order so they don't have to have a network analyzer per extrusion line. And this is just a slide stopper that can be manually raised, and this is in order to prevent the slab from coming into contact with the antenna subassembly itself. And it also provides a placement in order for consistent scanning when that occurs.
Here we have a design budget covering what the approximate cost would be when we split into two main categories, a single purchase category and a per extruder category. The single purchase category, we're not trying to specify in Mitsubishi that you buy a network analyzer for every extruder. Rather, the network analyzer that we specify is portable enough that it can be used at every extruder as they're doing testing. All they need to design is the main framework and the antenna design for each extruder. So if you're confused by the quantities, they are listed that way, extractional forms, for certain products that were specified in bulk packages instead of individually as needed. We added a miscellaneous column to the per extruder cost to adjust for the custom nature of that mounting arm for the antenna going along the rail. We'd like to give thanks to Stephen Knight and Julia Miller, the hauling manager and process engineer at Mitsubishi for sponsoring our project. We'd like to give thanks to Dr. Razavi for providing our team with the XRD and DSC testing results. We'd like to thank Dr. Bednars for carrying the course deliverables to our project needs. I'd like to thank Mr. Adams for helping us cut our test samples for our testing. And I'd like to give a special thanks to Dr. Taboon for taking time out of his very busy schedule this semester to help with our testing for both proof of concept and radar testing. Any questions?
First of all, you're all mechanical engineers, right?
Yeah.
That's right.
I applaud you for endeavoring to attempt and apply electromagnetics, which is not a class that you all take. So I really want that fantastic. I'm having an issue with terminology. Okay, you did what I saw you did was S parameter testing. Okay, to me radar is something different. Okay, and so if you were to apply what you did over the air transmitted S parameters. Okay, which we would do in an antenna range. We do that all the time for check testing a variety of different products and so on. So just be aware of that. However, your application where you're like you're doing like an S11 type test where you're transmitting off the same port and seeing what's reflecting back off the defective material. Okay, could be viewed as radar, but you're really still doing this one type test. So it's a ratio betterment on that end. How did you calibrate your test setup in that instance? Did you calibrate it just to where the RF cable's connected into the fixture, or did you calibrate internally without the material inside? How did you calibrate that?
Your first answer is how we did it. Dr. Sabuni had a eCal module, and we had run all the SMA cables into that before hooking it up to the
So you calibrated to the point of connection into the antenna.
Right.
So how did you deal with the error that came out because of the antennas and so on, or did you view that as it did not matter?
We did not account for that. For our focus being finding the peak differences, we assumed that those kinds of errors would occur across the entire spectrum. That was our focus, was just to find the large differences, not the smaller.
So the short answer is you don't believe it mattered. The short answer is you don't believe it would have mattered, which that's what I'm trying to get at. Did it matter or not matter? It didn't. And in your instance, it doesn't. I think you're okay with what you have. Calibrate the losses in the cable, the phase variances in the cable, and all that other stuff. What's happening internally into the chamber, that granted there's going to be reflections and all this other stuff that's happening in there, but it may not matter to you based on that. The other thing is did you have any metrics or data on the RF absorption or that of the material that you're testing, any of that information?
We were provided data sheets from Mitsubishi. However, the information that was on those data sheets really did not have a bearing on our work. There was a lot more of mechanical strength testing, the standards that they do with each sample to, more than what the sample actually measures.
But it was absolutely obvious that what you had done had detected flaws, right? So that was the key thing, correct?
Yeah.
You were successful in that end, so that's great.
Unfortunately, we would have liked to have tested more samples, but we're running into it.
Yeah. 16.
So in this case, we can see that a difference between the sample that is heavy and the sample that is not heavy. So how do you define those differences in terms of the peaks? It's like going to be 5%, 20%, because here we can see that directly. So how is going to be that process? And my second question is going to be just a change of magnitude in the peaks or also a shift of the peaks?
Okay, so firstly, I want to preface by none of us are experts in this. We kind of only know about it what we need to for presenting this as a possibility in testing design. Dr. Suridi would be the better person to ask. However, our understanding is that, for one, because there are large units of scale, we can't simply do a percent difference because take negative 40, for example, on that axis. It's not really the number negative 40, it's 10 to the negative 40. So, while it looks like as you go down the graph, the number's getting larger, it appears to be actually getting smaller in terms of the average measurement. We're looking to just see visually that graph on the right, that compared to the rest of the graph, there's that big distinction.
So this is an S31. Did you run the this is S13. Did you run S31 and get the same results?
We did not. It was inconsistent, just across S13.
I mean, all it is because your left side is basically a logarithmic scale. Okay, so then if you were to convert that to linear, you're going to see a very minute, small, tiny number on the side. But this right there indicates that there's a flaw in your product. You don't know where the flaw is, but you know that there's a flaw there. And so if you were to run it the other way, I would expect you to see maybe not the exact same result, but similar results. And that's where you go back to the calibration thing, and that because based on where the antennas are in the chamber, you may be getting different reflections based on how they're affected. Hopefully not, but you never know.
Yeah, so as to your question, we were seeing in the S31 the same process of there's peak showing defect.
Yes.
We just weren't seeing it the same, like, inverse way.
Yes.
If that makes any sense. We weren't seeing that it's going to peak at 7.4 gigahertz going in S31 just as it does in S13.
Was it around the same frequency range?
We had a lot of inconsistency for where it peaked, but we did notice a trend that below 40 gigahertz, we really didn't see that many major peak differences. It was entirely concentrated in 40 gigahertz all the way up to 10 gigahertz.
Okay, so that was a really great morning. Please help yourself to box lunches as Suzanne coordinated through Wearable. So lots of different varieties, and there's sodas and waters. And we'll be back in approximately 1 hour, so let's shoot for about 12:15 to kind of start funneling back in and get started back up for our last afternoon session. Thank you.
Let's move this table up. Can I use this one? Old Gonzalo's video, because then you can't do it. It's just like we're
We're good? All right. Sounds fine from here.
Yeah, it does sound fine from here. And his video was just as loud as mine, I'm pretty sure, so.
Right.
Okay. Fuck it. Let's put it on the front screen. Yeah, we'll just leave it.
Minimize.
Nature, like you mentioned,
Lifeline.
the nature of the project is different. You know, for you guys, it's all doesn't matter what you get. It's about it's natural. When you kind of never really have that.
There it is.
Find the possible solution that you do that. Although you were in bad shape, you very stationary. You think you really think too much about it. That was good. That was good. I was very impressed. I was going to see something. I was going to get a chance, but I was going to company. Yeah, I know. I was going to say that. I was like, because who knows? At the beginning, when you think on this project, who knows you're going to push you to the direction of your really activator and unknown. But at the same time, you can't dictate where is the solution. You can't dictate the solution is in the mechanical thing, microwave, whatever. So that's a genius part of this solution. It's really thinking out of the box, but at the same time, it's actually I really think this could be their, if they don't like it, take this lightly, they don't appreciate it. It's their box, but you guys give it. You found the solution. So it's not exactly the same thing yesterday. I know you can fix. Basically, sinking is nice. So basically, you have basically the action channel. And you have one
SolidWorks like motion, whatever motion is, and then the snipping to the tool on Windows you can record. So I just did that, and I got it some like video to get harder online. And then there's just the glad someone finally mentioned it. I'm so proud of that thing. No one said a word about it.
Because all alignment actually there's two spectrums. And then the only way to keep that is at the top. So if you, because there is a slide on it, like that all, leave the expecting, like, a increase in
Yeah, I mean, but first, like, you guys,
and then, you know,
heat mapping,
it's really,
I was like that myself.
like, that is our system. Like, we're gonna have a spring to close the latch once the shaft is in place. I know what we're going to get, but I'm wondering what we can bring up, like, how to answer is, how do you know the shaft?
No, I was gonna.
From, like, and I
I was
designed
gonna
it to
ask
have,
you guys, like, what if you did want to put it into a commercial application? So would you like a buffer on
so,
top of the house?
as long as the shaft is already in that half circle, once pressure is put on it, it's going to slide or drag the shaft. So it will, as long as it's in tension, it should not be unless unless this thing's fucking it should generally sit there. So that is those are the questions. Not knowing I have to have every so no one has the exact plan for this. So it'll be funny to watch the senior project. I mean, so it'll just be really just be I am tracking efficiency and we'll be running it
Because I saw that it was low, and then I thought, I bet they actually got it up, the efficiency.
Give us about
also, I did it, like, we ran our shit, like, not that, like, and he said, sure.
I mean, for me, I would just start your PLC and compare it to regular, just looking at combustion engines at 68% are already above.
Oh, that's our things that he said. He said,
It's probably the same thing too. You're losing all the instruction errors at that.
no, we made sure that he literally just told us, besides those two jobs, that just goes, because I did you get some shakes and just which to be honest,
I didn't see you and I was concerned. Well, I got your email. You said you were going to that's fine. Thanks.
but it's not, actually just haven't heard of it, so I don't explain.
I didn't see it.
So that's what I mean. Some of these steps are this one.
I didn't give it to anybody. I left it right there. I'll see if Nick has it.
need to, if you're gonna need to glance at the slides, stand somewhere where you can glance at the slides. Yeah, that's fine. Hey.
Not worth it.
Fair enough.
I remember the title. I think I saw that. But we have
So to start off, a little introduction. As we all know, mining used to be a really big part of the infrastructure of the economy in the Louisiana area. Somewhere around the 1960s, it was abandoned and Saddam Hussein. But then just disappeared completely. Left little pieces of itself in the form of abandoned mines that just surround us today. But who cares? What's the problem? We're not using the mines, so well, what's happening is water is entering these mines through surface fraction. And once the water gets in, it's picking up a bunch of minerals and fluids and depositing it into places such as the Susquehanna, as you can see here. So what we need to understand the geometry of these surface fractures. People like Dr. Whitman can create hydraulic models to understand how the water is flowing in them, how much water is flowing in, and if the water can be prevented from flowing in. So what's our part? We started this project 2 years ago in 2021 with the initial goal of making a robot that can travel into these surface fractions and use video to map the geometry. We completed our first prototype in 2021, as you can see here. For our senior project, our goal was to completely redesign and improve this initial prototype and actually get it into the fractions collected. Just for reference, so you have an idea of what these fractions look like, here's a picture of the one that we went into at the end of the semester.
So for our requirements and specifications, we focused on three main design options, and that was size, adaptability, and self-containment. So we wanted a compact design that was lightweight, durable, maneuverable, and modular, because we don't know the geometry inside these surface fractures, so we have to be able to adapt to maneuver into them. We also wanted self-containment, which means internally powered and wireless communication. were questioned about why we wanted wireless communication, and the reason is we don't know the geometry inside these fractures, so there's a high possibility that a tether could get cut, gets snagged around something, and we don't want to lose power or communication with the robot.
The work breakdown structure is divided into 3 different parts: the mechanical design, which includes the component we bought and the parts we designed and built; then the electrical design, which includes the sensor circuits, the power circuits, and information circuits; and finally, we have the software design, which includes the motions and the basic coding. For the schedule, as you know from the last semester, we almost finished the robot. So this semester we focused on improvements such as including a camera, including more movements, or improving the ones we had. And we also focused on testing, with our final goal of going inside the fraction. In terms of money, the actual cost of this prototype was $3,670, and we think that we could sell it for around $5,000, but this price would be much lower if we use mass manufacturing because the cost would be reduced.
So for the epic portion of our project, we deemed ourselves to hold paramount the safety, health, and welfare of the public. The reason we respond to that is because the whole purpose of this project is to go into these fractures and help with the pollution into the Susquehanna. So we also found some regulations about having lithium-ion batteries inside these mines. Most of the paperwork talked about charging batteries and having damaged batteries inside the mines. So before we enter these fractures, we make sure to do a full check over and make sure all the batteries are fully charged.
Hey, wake up! I know that this part has been a bit boring, but believe me, this is going to be very interesting, so keep an eye on this.
Okay, so let's start off. We're going to talk about the mechanical design of our project. So as you can see here on the top, we've got an image of a complete robot, and we also have everything down on the stage. The main design is split into 3 parts. We have the head, all the segments, and then the tail. The head, its main purpose is to house and mount all the different sensors. Most importantly, it's got the camera module, which is attached up top. For the segments, they control the motion. Each of them had a servo motor and a battery. You can look at the picture on the right, and you can see we have an open up segment, how the servo fits in, and how the battery fits underneath that. And then the tail, the main function was to govern and control the motion of the entire robot. Like the segments, it also had its own servo motor, and underneath this front cover, it also housed the battery. Moving on to the electrical design, here we have our PCBs and our schematics for both the head and the tail circuit that we designed. For the head, like I said, the main purpose was to interface and control all the different sensors. We didn't just have a camera, we also had sensors such as an eye view and a magnetometer, so while this robot was in a fracture, we could get real-time orientation data of the head. Not only did it control the sensors, it was also responsible for communicating back and forth with the controller. For the tail, like I said, the main purpose was to control the motion of the robot. Most importantly on the circuit, it had a current control. The reason why we needed this is because we wanted to protect all the components from large current spikes that come from the servos. We wanted to make sure nothing got overheated, and we wanted to extend the life of our batteries by limiting the current.
So for the design of the controller, we have our fully assembled controller on the left and our circuit board on the right. The purpose of our controller is to communicate with the robot using joysticks and buttons to gather information, and we featured a display in the center of the remote. This display helps us get information such as battery life and the current draw from the motors.
So some design for the other part, like we said, one of our main goals was to have wireless communication. In order to do that, we came up with the idea to use wireless repeaters, as you see here. The idea for these is they'd be attached about every 4 or 5 feet on the rope that we had tied to the robot, so if the controller was trying to communicate, it didn't have to send the signal all the way through the fraction, it just had to send it to the first repeater, which then bounces down the line through the fracture, so the robot and the controller can talk together. I know what you're thinking, this just sounds like a really complicated way to do a tether. Why not just do a tether, something's tied to the back? Well, in reality, these repeaters actually simulate having multiple robots, multiple snakes in these fractures, all talking together in a network. That way they can position themselves so you can still get communication out to the surface.
So on the right side of the screen, screen, we have our water-resistant hose. We were questioned about what if the robot comes in contact with water. So we came up with a solution of putting it in this hose. The hose has a fixed end on it that is sealed with gasket material and has a plexiglass front plane on it. The reason for the plexiglass is so once we put the robot in it, the camera can still gather information.
The testing plan was divided in 4 different stages. The first one was the component testing, in which we test every single thing alone for knowing if it would work correctly, such as, for example, the camera, the motors, etc. Then the second step was the basic movement testing, which we also used it to improve those movements. Then the difficult terrain test, that is the one, the picture down there. And we chose terrain with high grass and some slopes. And finally, our main goal of this semester to go inside the surface factor.
Okay, so now for our results from initial component testing. Like we said, one of the most important parts is the current control. So as we can see here, we've got a graph of our current that was being drawn from the motors while the robot was in motion. Our current control at this time, our max was set to 4 amps. And as you can see, there's no those perfect horizontal line where our current control circuit is clipping in and controlling that circuit to make sure everything is protected and nothing is overheating. So current control, that was a success. For communication, like I said, our idea was to use repeaters. Unfortunately, while the idea was good, the execution didn't work out as well as we hoped. The main reason for that is that we were really limited by the actual radio chips that we decided to use. At the time, we didn't know, but these radio chips can only read or write data at once. They can't do it at the same time. And in switching between those modes, there's a really long dead space where the chip actually can't be running. So this wasn't a problem when it was just a robot and the controller, but once we added more radio chips into the network, the chance that the signal got through really decreased because of this dead zone. Even though this was the case, we were able to show that these repeaters help communicate around obstacles, such as a hallway in start, where the robot and the controller couldn't communicate otherwise. So in order to improve this problem, all we have to do is find better, higher quality radio chips, which are capable of faster communication.
The picture at the top, in which you can see Jacob and me sitting on the ground, is taken from, it's a screenshot taken from a video that we recorded while the robot was moving. So this way we knew that when we were going to the surface factor, the robot would be able to record while moving as it should.
So for our water-resistant testing, what we ended up doing was putting a paper towel into the hose and putting the hose underneath the faucet and bending it every which way, waiting for it to spring a leak. Once we got done, we pulled the paper towel out and noticed that it was completely dry and the test was successful. But unfortunately, once we put the robot into the tube, it had a real snug fit, which we wanted, but the material would not bend or stretch. So in the future, the idea is going to work, but we have to find a different material for the hose to be made out of.
For the difficult terrain testing, we have a picture on the right of the 3 of us working on the robot just before starting it, and also a video in which we show how the robot is able to turn around to full revolution, and also is able to go forward in a straight line. You will see it just in a second. It's not very fast, but it's consistent, so these are only 2 of the movements that it can do.
So next we went to attempt to enter the fracture. We have 2 videos. The first video is from outside view of ORMR making his way into the fracture. The important thing to get from this video is that ORMR is able to enter the fracture by himself. There's no external help needed. And this is important because if ORMR can't get into the fracture by himself, how's he going to move inside the fracture by himself? So that's the importance of this first video. In our second video, we have the camera feed from ORMR as he's heading in. So as you can watch in the video of the camera, he ends up running into rocks and sticks, and he's able to maneuver his way around rocks and sticks up to a point where he gets caught.
Don't go much further. You know how much you grab. Yeah. So
as you can see now in the video, ORMR has hit a rock and he is stuck, but he is able to maneuver his way around that rock, and making that maneuver got him stuck under a second rock. Now, it took him a little bit longer to get past this rock, but he is able to climb on top of it and get us some good video of this unknown geometry.
So as you can see now, we're on top of the rock. I'm going to start moving the camera around and get different angles so we can understand what the inside of these fractures look like. As you can see there.
So now I got 3 screenshots from the camera recording. We grabbed these 3 screenshots because we found them to have the most information about this surface fracture. We talked to Dr. Whitman, and he concluded that with ORMR's help, we could have a good possibility of getting the unknown geometry all mapped out and helping with the pollution problems in Susquehanna.
To sum up, we have to say that the return area is in danger because of abandoned mines and the pollutants that enter and flow into the Susquehanna River. But we can also say that we have a solution because thanks to ORMR, we are able to measure and take information from these surface fractures, which would allow people such as Dr. Whitman to make the hydraulic maps and try to avoid the water flowing into those mines.
We'd like to give some acknowledgments. First, we'd like to thank Dr. Whitman for approaching us to the idea and the problem. I'd like to thank Dr. Zhu for being our advisor and helping with robotics. Dr. Young for some help with mathematics and software. Dr. Wu for helping with 3D printing and manufacturing. And finally, Mitch for letting us borrow things. Here's our references. After all the presentations, if you want to see a demonstration, you can come see us afterwards, and we'll be happy to show you a little bit more of what we can do one-on-one. Any questions?
So the radios that they were using, what's the frequency? 2.4 gig. And it sounds like they're basically a simplex radio. Okay. And did you have any luck finding a full duplex radio?
At the time, which we actually figured out that this was a problem, we only had about a week left of the semester, so we didn't start looking, but that is
So advice is you're probably going to look for a full duplex, and I would recommend that you have a different transmit frequency and a different receive frequency. So you don't transmit over 2 frequencies with an offset. And you can find them. They're out there. Okay, they're out there.
Is the video help guide the behavior of the snake, or is it just for recording? Is the video camera help you guide the behavior of the snake?
No.
Or is it just for
right now it's just for recording.
So for the current control, I think that was a great feature because even that's actually because that's pretty much it. When you were doing the testing, did you notice any like overheating of the servos?
The servos themselves, run some of the components on the board. They're pretty hot. So the moving forward,
Keep the current control tall to prevent heat overheating. And this feature, it doesn't overheat to the point of overheating. That's a great feature.
As the robot crawls over the rocks, can there do something from on?
Alright, so play this video. At the back, we actually tie the car over here just to make sure that
If it goes inside, kind of, it's a start, here's what we kind of look at.
Here's the question.
When you think it's a start, you think the rocks. Yeah, that's what I'm saying.
Down the road.
It's part of the design.
No, so ideally it would be able to move it like back out of the room, have that on development of the motion. Do that, and we want it to be actually safe that we can have it here today. We didn't want to lose the expense of a lot of whole every day.
What was the
What was the material that you used for the
so I was doing research into like a shrink wrap or some kind of tape to wrap around it, and it seemed that the different change in temperature changed with the elasticity of it. So we didn't want ORMR moving his way in, and as he heats up, the shrink wrap getting tighter and stopping him from doing any more movements. So we went with the tube option.
Another thing is we needed the water receipt to be temporary because we need to be able to insert and remove them to do things like change the batteries and make repairs. So we didn't want a permanent solution.
So what's the difference between what we've done with the soft robot kit, which is available in commercial?
So the main idea of this is that it would be cheap, disposable, and you can have many of them go in structures all at once, all communicating together. So you just send like a fleet of robots in to get all the data that you need. And the reason it's a snake is that you can easily adapt to whatever terrain that you need. It's not like a robot specifically designed to perform tasks because we don't necessarily know what it has to do in this. It needs to be able to kind of do it all. It's not great at everything, but it's good at most things.
$5 grand is not cheap.
Yeah, I was going to say that. So could you predict that if you could mass produce this, let's say you make 1,000 in a batch, and what would you see the cost, the average cost of each?
Yeah, so the 5,000 was looking for this, what we have here today. So I think in theory for mass producers, we get it down to 500 bucks.
The 3D printing was very expensive, so this is a part where the cost would be reduced a lot. And also buying a lot of servo motors, which was the most expensive part, would reduce the unitary cost. So.
Thank you.
No, that's one I brought.
Oh, okay. No, you're good. I didn't know you brought it. I thought there was one up here.
No, I don't know. I think the one that was up here was Lucas's.
Oh, okay. That's fine.
Do you want me to open that?
What?
The mold up?
He's got it.
Oh, he already got it.
He should got it.
Should have. You ready? Good.
Yeah, on you.
All right. We are RPS for Recycled Plastic Structures. I'm Stephen Gazy.
I'm Michael Czerkowski.
And I'm Owen Breisch.
So just a brief introduction and reminder of what our project is. Recycling is the #1 way here to take old garbage and to make it into something new. So our design for RPS is to take garbage and old plastics that haven't been recycled yet and put them into our machine, melt them down and put them into this mold and make modular bricks that are stackable and interlockable to be put together to make a building or a small structure that could be used for disaster relief or emergencies, stuff like that. Our bricks have been designed and we've been testing them to withstand the pressure of being able to be stacked up high enough to make a building or a small room. And this is a proof of concept that we are able to reuse PET plastics into something that could be used again. So this is just a quick breakdown of our schedule. In the fall semester, our main idea was getting the brick design to work by itself and having interlockable bricks that stack and fit together nicely. Where this semester we focused more on building the actual apparatus with the plunger in it and the actual testing to make sure that everything's working out and we're getting proper molds from the machine. This is also just our quick budget. The main part of our project was the heating bands to be able to melt the plastic down and the controllers for that. But also we came in pretty decently over here. We're under budget, so that's a success for us. So we do have extra money to spend because we did have one heating band break on us, so we had to order a new one. And we used some of that extra money as well to buy a heating pad to set the mold on top of. That way when the plastic is being put into the mold, it doesn't cool too rapidly, because that was a problem that we had early on in the beginning. So these are some previous designs that we had from when we started the project, and our goal was we kept it very similar to what we originally stood out for, of having the brick with the male and female cleat system on the end, and also having the studs on top with the holes on the bottom like a Lego brick. And that was also our first design of the apparatus itself, which is very similar to what we have today. We're going to go to, Michael's going to talk about, or Bowman's going to talk about the designs.
So kind of just going off of that, this is what our actual injection apparatus is. Up here on the far left, we have a picture of the actual SolidWorks model. This is kind of excluding all of the electronics to it. But you can see one thing that we added was we have slots for the PIDs, and we also have a slot for a light switch. Kind of just moving forward to the other two pictures, they show what the actual thing looks like with all the electronics, the light switch, the PIDs, and you can kind of see the wiring for the relays in the back. One thing to notice between the two actual real-life pictures is one has the blue kind of cover on it. That is a barrel shield. We'll get to that later. And yeah, this is kind of a setup for when we would actually be trying to push into the mold. So the second part of our project was the mold itself. It is comprised of 3 different parts. So as you can see, we have the SolidWorks model above, with the piece on the far left being our universal female, and the other 2 pieces connect into it using steel pins. And then you can see below each of the model pieces is their respective real-life counterpart. The pictures are looks a little crusty because that was after we pushed some plastic into it, but we did the best we can with that one. So we know one of the major concerns from the fall was safety, so we kind of really wanted to add that slide into our presentation. One of the first and main things is just gloves. If you're working anywhere near the barrel and just kind of were close to the contact with anything hot, we wanted to just make sure we have them on. Additionally, I mentioned before the shield, the bright blue thing on the front of the apparatus. We have a picture of us temp gunning the shield there. So that's running around 160 degrees Fahrenheit compared to the barrel. That's like 500 degrees Fahrenheit. So I'd much rather brush against that than the actual barrel. But in addition to that, we added a few electrical parts to it. So we have the system on and off switch, which was just general safety, and then we were always plugged into a surge protector. And lastly, we did it in a room with ventilation, which was also important.
So moving along to our testing categories, what we first wanted to test was the electrical components, just to make sure that everything was communicating with each other, all of our heating bands were working properly. And once we got everything put together, we went on to our temperature control testing, which we started at about 500 degrees and went a little up and down from there to see like what was the best temperature, what results we got. So we took 500 as our good point for melting the plastic into the mold and then filling it out nicely. After we did that, we also went on to the mechanical testing, where we put the plunger and everything together and made sure everything's flowing properly, everything's getting into the mold, there's no bubbles, just the physical aspect of the mold itself.
Electrical testing. Here we have basic circuit setup confirmation. The circuit's right over there. Very simple. Not like past projects are just up here. Just a couple of PIDs and relays. Here's a chart showing what we tested and passed. The 2 things that didn't pass were the 1-inch heating bands and the heating pad that we plan to put on the mold. Picture up here is that first heating band. It burns up as soon as we power it on. Not good. And that heating pad there, it's only about 1 inch by 2 inches, actually really small. They said that it would have been able to provide the right amount of wattage, but it just didn't permeate through the mold at all. And an honorable mention for the first setup confirmation was a blown relay. We shorted it out and it didn't work after that. Temperature control testing. We have a couple pictures of the PIDs, a hot plate, and that picture on the far right is the temp gun showing the heat distribution of the mold on the hot plate. You can see that it's providing enough heat through the bottom of it. We set up the 3 PIDs to control each section. We have we were going to put one on the mold down at the bottom, but as we said, the heating pad didn't work, so we went to a hot plate, which we didn't use the PID for. And this nozzle down here is controlled separately from the barrel, and that provides us with more variability so that we can keep them at 2 different temperatures and control them separately. Just right here is a little bit of an explanation of our testing and where it led us to for the mechanical section. The barrel, we decided we were going to invest in spacing. The nozzle, we moved to a 3-inch heating band because the 1-inch heating band didn't have enough wattage going through it, and the mold, we went to a hot plate.
So, kind of like Michael was saying, when we're jumping into our mechanical design, we did do a bunch of different configurations with heating bands. This doesn't just include kind of testing them their temperature-wise. It was kind of their placement on the barrel. We had 2 of them very close together, and when we added a third onto the barrel, we kind of spreaded them out to hopefully get a more uniform degrees across the barrel. In addition to that, like we said, our smaller heating band ended up burning up, and the whole one didn't work. So we kind of made a makeshift, as you can see, we made a little makeshift spacer so that the 3-inch heating band would heat up the nozzle. So going off of that, we also had issues with the plunger. It is aluminum versus our barrel, which is steel. So when we originally had it turned, it would still fit in, but once it started heating up, it would expand and get stuck in the barrel. That was a setback for us. But now it does fit, and yeah, it fits. The barrel, it does also have a little bit of non-uniformity to it, so it's not completely circular. So we also contribute that to a little bit of our issues with turning the plunger. Next, we do have stand stability. Once we kind of initially made it, we didn't have feet on the front, but we kind of realized it will be a little front heavy with the heavy steel shielding and the barrel in front, so we added small feet. And then last but not least, we did nozzle length adjustments. It was originally like 2 inches longer, but we were realizing we weren't getting enough heat to tip the nozzle, so we just pretty much chopped it around and measured itself off. So kind of what our procedure was on the day that we planned to hopefully inject something. We would start by kind of loading the barrel up with however much PET or plastic that we decided was enough. From there, we would then plug in the heat injection apparatus in the hot plate. From there, we would then set the hot plate to our preferred temperature, which was setting 1 or 2 around 300 degrees. And then we would set our barrel inner nozzle to around that 180 to 200 degrees Celsius range. We would wait for that to kind of reach that set point and stabilize. From there, we'd kind of push the barrel temperature up to our final range of 240 to 260. And once that got up to that temperature and stabilized, the nozzle was ready to kind of be switched into injection mode, which is around that 245 to 255 degrees Celsius range. So I guess what everybody's been waiting for. There were a few failures. So the 2 pictures on the left there, they kind of show those are the instances where the plunger ended up getting stuck in the barrel. So we kind of just had to shut the whole thing off, and we came back the next day, and we have what we call like little pucks. You can see the picture on the top is a fairly melted piece, as opposed to the one below it, where you can see there's still actual plastic not melted. And then one of the better results is the picture right here. We got it into the mold, but the hot plate was a little too hot as we were trying to get the kind of the rest of the mold to heat up, and we ended up cooking it. But we did get a good 1/4 inch into the mold. But once PET is kind of overheated, it's extremely brittle, and it
bunch of pucks that we had in the box there. One of the most important ones here is we soon realized that it was going to be very difficult to get into the mold, so we scaled it back a little bit, and we just wanted to get into a small cylinder that we put on the hot plate. And it wasn't quite up to temperature, but we got good penetration within the barrel, and we were able to push it out into the cylinder.
So kind of some of the setbacks, I mentioned a few of them already, and they were mentioned across the presentation. Plunger was a big one, and it stopped several different days on just doing anything for the rest of the day. We had issues with the heating bands, not only replacement, but some of them actually going up in smoke. Lone relay, it's the stand stability, stuff like that. Non-uniform plastic, another biggie.
Coming to lessons learned, we learned a lot from our experiences. We did a lot of testing and a lot of varying the procedure, varying temperatures. There was a lot of work to be done in between test attempts too. So we've discovered that injection molding is quite intricate, and it was very hard to simplify and dumb down to something that we can bring within our means. And we may have shot for the moon on this one. However, things to do differently that would ensure a greater chance of success would be an aluminum barrel, because we noticed that it was hard to penetrate the cross-section of the barrel with our heating bands. Higher injection pressures, that would help with, if we got to an acceptable, it would lower our acceptable temperature a little bit, because we did often burn plastic. We're trying to get it within a certain range, and the range was actually surprisingly small once we started looking at it. And a more thorough sensing method for the PIDs. We just have the thermocouple welded onto, or two nuts welded onto the bottom of the barrel down here. And that's actually quite far from the rest of the heating bands. So heating bands would put a lot of heat into the barrel, and it doesn't transfer as well with a steel barrel versus an aluminum barrel. So we'd end up cooking the plastic up here, and the plastic down here isn't melted properly.
So kind of in conclusion, we were not really successful with what we set out to do, but we do think with some of the stuff we actually did get, it's fairly strong. We didn't do actually any testing on it. We don't have very many samples, but we think this is a good proof of concept for additional recycle applications, not strictly just like small bottles and stuff like that, something that could potentially bear some type of load or anything such as that.
In the end, we were unsuccessful. However, with more time and more variations with it, we probably could thread the needle and get a clean injection. However, we just weren't able to complete it with this.
This is a list of the resources that we used. We included that in our presentation. And we definitely want to put a thank you out to everybody at Wilkes for giving us this opportunity to create this project and work on it. We also want to thank Dr. Moo for being our advisor. We also want to thank Mitch Adams for his assistance building it and everything that he's done for us. And we also want to have a special thanks to Matt Haber and Caden Dearborn for their help and the contributions for this project. Does anybody have any questions?
similar to the FilaMax project, right? I mean, you guys similar, right?
Yeah.
Are you using the same kind of temperature AD device? Is that?
Yeah, we're using 3-inch lead bands that are made out of.
Because they have similar kind of carry controller for the temperature.
Yes, yes, that part is very similar. The main difference is usually is the actual method of they're doing extrusion while we were focusing on injection.
Yeah, I mean, like for this to even work, you see, you need, like for them, it's like they can't just melt slowly like a nozzle, but for you guys, you almost need a container to collect the melting and then inject at the same time. You can't just be like for them, gradually, you see what I mean? Like just based on the temperature of the nozzle to try to.
Yeah, I mean, that was kind of the goal. We kind of tried to load it up, get it all to around a.
So that wasn't, because I guess it's because you don't have a heated container to collect it, keep it melted, right?
Yeah, that was kind of the goal for the hot plate, to kind of keep that mold.
Because that's like, to do that, that's lots of heat. That's
Yeah.
like a tremendous amount of energy there.
Yeah.
That might be the reason why it kind of broke down eventually.
How many water bottles did you have to melt down for the testing phase?
It was a lot. On any given attempt, it was between 30 and 50 water bottles. So 30 was about like 3 inches from the bottom of the barrel. So,
And they were all different brands. Did that give you any issues with
no,
consistency?
we cleaned them all pretty properly, but all very fine. And the material was very consistent.
Any other? Usually I have to kind of run on. Okay, thank you.
Oh shit. Oops. Fuck. Ask me that question. Damn it. Fuck. Oh, here it is. Okay, I got it.
Okay, guys.
Good afternoon, welcome to our project presentation. We had a company-sponsored project by CornellCookson, the cardboard automated rolling place. I'm Daniel. I'm Dominic.
I'm Brad.
So first, what is CornellCookson and what do they do? CornellCookson is a leading manufacturer of garage roll-up doors and enclosures for industrial, institutional, retail, and commercial use. They have two locations, one here in Mountain Top, Pennsylvania, and the other one out here, Arizona. Our project benefits multiple plants. What is our project? Our project is to create an automated process for rolling the cardboard, as well as making the process more efficient and making prevent. Right here, you can see an image of the actual prototype that we created. This is fully functioning and wilts the cardboard as expected. Brad will go into more detail about every component later on in the presentation.
For our requirements and specifications, we were building off of the previous machine that Cornell currently uses to roll cardboard. The main requirement that they tasked us with solving was fixing the issue of having to prevent every single piece of cardboard that they could roll in. This was our main requirement. Additionally, we kept it as much similar as possible. We used a similar size motor, similar fuel reduction, to keep consistency between the speed of the driven roller. Each piece of cardboard is set for this is a quick process section of what cardboard looks like before it's rolled. The outflow of this cardboard needs to come out the back. This is ideal for the future automation of this project. Makes things a lot easier. The current machine that out in front of the machine, which makes that significantly more challenging to automate. And lastly, we want this machine to be safe. There's people working with this machine every single day. It's something safe to be around and use.
So this is the current process of the rolling process that is used in 3 bays. It's all basically the same. However, the location of the cardboard is different per day, just depending on where. So initially, on the left picture, you have the worker putting the first 2 inches of the sheet of cardboard into a metal channel, in which they then vertically crease it up, the first 2 inches, and then feed it through the machine. The machine then actually feeds it back into the person, where they then place it underneath the machine for storage. When we did our testing, we analyzed that it takes about 41 seconds between grabbing a piece of cardboard and placing it underneath. And we expect that by eliminating just the pre-bend alone, we can save about 10 seconds in the whole process. That would save about $10,000 a year. And based off the 41-second time for rolling each sheet, that takes about $35,000 worth of labor costs. That was estimated by the amount of pallets of cardboard they order every year. So this was the prototype model that we had. As you can see, we have a vacuum gantry system, as well as a pallet of cardboard, the roller box that we designed, and a rolling cart. So the idea would be the vacuum gantry system would lift the cardboard off the pallet onto a rolling table, which would then get fed into our roller box, and ideally fed out the back into a cart. That cart is designed to hold all 64 sheets of cardboard found on each pallet. This is a reverse view of the model that we had previously. As you can see in the left picture, that's the opening where the cardboard would come out of, ideally, as well as feeding into the cart there. The opening was made for the minimum and maximum values from our testing. We noticed that depending on depth of the cardboard protruding at the back, it would change the angle. So we made sure that the opening was big enough to allow for both maximum and angle. And this is just the OSHA safeguarding that we designed. We designed an 1.5 inch opening to feed the cardboard, and by their standards, we have to have about 12.5 inches of distance between the entrance and the danger or pinch zone. So we designed it to be 13 inches, and utilizing an angle to both reduce materials and also to ease into feeding the cardboard, as Anya will demonstrate later, as well as our control panel, motor, and speed reducer. So this is the building process that we had. The top left shows the legs and the bottom plate frame all attached. The bottom left shows the side plates, the bearings, and the top support rails added on. The top right shows the hoods and the feeding table installed, and the bottom right shows the control panel, speed reducer, and the motor also installed, wired, and ready to go. So this is the final product that we made. As you can see, we have stainless steel guardings. We chose stainless steel to reduce oxidation that might occur in the workplace. Cornell always has their garage doors open, whether it's for shipping or just it's a nice day if they want to have some fresh air. Ideally, we will spray paint the whole frame that isn't stainless steel, but in our prototyping phase, we do not get to that point. As you might be able to see, we have a curled metal lip for the feeding. That's to reduce possible injury of the operator rubbing their hands or whatever on the sheet metal itself, because it's very thin and could be razor sharp. And as you can see, we have the 1 or 2 inch gap for the exit feed, which the cardboard will exit out of.
So here we have the updated process of rolling cardboard. This is what we came up with and we designed. So a couple of key takeaways from this video that I want you to observe is I fed the cardboard directly in. There is no longer a need for a pre-bend, and with the machine all testing found that there was no pre-bend at all ever needed. The cardboard goes in the front, it comes out the back, which is what our ideal situation for automation is. Ideally, there's going to be a cart back there. There's just a pile of scrap and everything. That's just where we decided to build the machine. Additionally, with that front cover, that angle on it, you can see as I go to place the cardboard into the machine, I actually use that front angle to guide down onto the tray so it's easier to load the cardboard directly. And one more thing is you also notice the height of the machine is right around my hips, which on the next slide, you can see in comparison to the old machine. So the old machine, the in feet was about halfway up my thigh, which is around 24 inches. And that is not kind for the worker's back, as some of the workers are much taller than I am. I have to bend down to be able to put the cardboard. Our new machine is up to my waist, the tray is at 36 inches, and the taller workers love it. They can walk right over, take a piece of cardboard, put it right in, and they're good to go. This made the cost down to an estimated $12,000 per year. So then we start to get fancy and take out rollers. We got down to a 2-roller configuration, which is the one that you just saw in the video, where it fed in the front and came out the back, as well as a pre-vent needed. That took 12 seconds to do and estimated to be about $10,000. We then decided to try one more configuration, and that was with the main driven roller and one roller directly underneath it. When it was fed in, the cardboard never actually was able to decrease because it was just being fed in a straight line. So therefore, we don't have any testing results for that. So now you might be asking yourself, the whole idea of this is to be fully automated. Where's the automation? So initially, we had to fix the current machine to require no prevent, so that way it could be put to an automated situation. So we sat down and talked to Cornell, and they told us, okay, go out, talk to a couple of automation companies, give us the results, tell us what you can find. So we talked to 2 different companies, the first one being Coldbus, and they have a machine called the AF300. This is specifically designed for cardboard feeding. We place a pallet of cardboard on a lift table, a vacuum gantry system will pick up a top sheet, load it onto a table with rollers, and be fed directly into the machine. We are quoted approximately $150,000. That includes the price of the machine, the shipping, the installation, and the training. That will also take about 3 to 4 months to come in. So I'm going to the next company, Favorite Industries. They're more of a middleman in the process, and they can get us just a vacuum gantry system. So we'd still be responsible for a lift table and a roller system to feed into the machine. Just the vacuum gantry system alone would run us about $40,000 and have a 3 to 5 week lead time. And then the last option is manufactured in-house. So we leave it up to Cornell to just fully design their own automated system, which has the potential for time savings and money savings. But at the end of the day, probably Favorite Industries is what they'll go with, just because it's a cheaper option and the system already works. In conclusion, CornellCookson is satisfied with the job we did. We took the old machine and we were able to eliminate the prevent from it, saving approximately 30 seconds off the process. This will lower the cost by around $25,000, and this machine will be implemented in Mountain Top as well as Goodyear, Arizona. We did hand over all the information needed for the automation, so it is now up to them to make a decision whether they want to go with a pre-built automation system or work on making their own. And some acknowledgements we'd like to make are Brian Kleist, he's a supervisor at Cornell who gave us this project. Dr. Zhu, who was our project advisor and helped us. Mitch Adams, who gave us advice on how to do the machine, as well as Con Beaver, Jeff Wilson, and Tim Combs, that are engineers at Cornell, as well as Michael Czechoslovsky, who helped me with the building process as an intern at Cornell. And then, so what we have here on the table is, as Dan showed, this is what the cardboard looks like when it's on the pallet. And it is half-inch thick cardboard, and I'm trying to bend it right now, and you cannot really bend it. So this piece was actually from that video that we showed. That is the rolled product that we came up with. And if you look at the front, you can see that there's a series of creases. You look on the back, you can't really see any creases. But the main idea is just with these initial creases here, it makes it that they can lay it in the cradle, and when the door gets laid on top of it, the way the door pushes over, and they take the banding, and it finishes off into a circle, and then the door is wrapped and protected for shipping. Any questions? So in the original process, they needed pre-done this cardboard. It does not need pre.
What would happen if the cardboard is put in at an angle?
So,
do you have a safety feature to stop it, or?
yes, there's actually a load sensor built into the control panel itself, so that if there is a major jam in that instance, it will shut itself off. There are also reverse features on the control panel, so if a worker starts putting cardboard in and they're like, oh no, I did it wrong, the machine's not being happy, they can switch direction and the cardboard will back itself out.
So if something, if the cardboard is stuck inside, can you shut it off and do a manual back off it? Is that possible?
So there is no function built into the manual backup. It would just be on the control panel itself.
But they can back
You would have to take off the chain to reduce to do a manual takeoff, but yes.
I would think that's pretty rare, right? That's not,
Yes.
there is a possibility of something actually gets stuck there and you want to be able to.
Yes. And we do actually have a crank that you could turn the machine over by hand. So if that were the instance where, say, the control panel shorts out or something, and there's a piece of cardboard jammed in there, they can't get it out, we actually do have a crank that they can disconnect from the motor and then back it out by hand.
Does the motor eventually have like a current control to prevent the next lanes stuck and then something so that
Yes.
it shuts off itself?
Yes.
It has that feature?
Yes.
So, yeah, you successfully demonstrated, you sped up the product from 40 seconds to 11 seconds. Did you test the feed speed? Can you go even faster?
We didn't actually, well, we could probably potentially go faster. We just didn't want to play around with the gear ratio too much. But
The speed will also come in time with what the automation system will actually entail. So how fast will the automation system feed, and then can you match that speed if it's faster than our machine? Because that's what our machine is built, like the legs are just A-frames of angle, so we can raise or lower the weight of our machine depending on where the feed of an automated system is. So if we need to speed our machine, we'll try to speed our machine.
So in theory, if you had it go faster, you could just speed it up.
Right.
it wouldn't be a dollar, it would be a gear ratio change.
Okay, everybody, so that completed our senior projects 2 groups. So we have one more group left to present today. This is a senior projects 1 group. They're pretty much demonstrating their design this semester, and then when we see them again in December, hopefully they have their built and tested prototype just like all the other groups.
Hi everyone, my name is Henry.
I'm John Vito.
Payne Rosaski.
No, Matt
We are the only group for senior project one spring semester 2023. And today our project will focus on designing a mechanical device called Lifeline here, which is specifically designed for linemen who work on wooden utility poles. And here's our full assembly CAD model for the current state. Moving on to our goal, we designed a planning to build a secondary climbing protection system for minimizing the risk from falling, and the device is expected to be lightweight and easy to assemble. Some general information about utility poles. In the U.S., there are approximately 180 million utility poles, and many of them are located in areas with poor accessibility, making some advanced methods like bucket trucks impractical. In this case, linemen have to climb up poles directly and perform their work, spend a long hours to perform their work. So the utility poles varies in height from 30 feet to 120 feet with their that got injured or killed on the job each year, which make it one of the most dangerous occupations to work with. So what is Lifeline here? It is a portable lightweight collaboration device with a locking mechanism and is designed to firmly attach a rope on the wooden utility pole that help the lineman to prevent the lineman from falling. And here is a sketch how the system works. So there will be an extension pole that brings up the device to a desired height, and pulling rope one that it actually have to lock the system, meaning the shackle on the left side and the latch system on the right side connect together. One end of rope number 2 on the left side will be knocked into the shackle. One end of rope number 3 will be knocked into the latch system on the right side. The other end of rope number 2 will go pass through a small loop of rope number 3 and go down, then connect to the rope ratchet. Rope number 4 on the right side will be used to release the locking system when the job is done.
So at this point, we have connected our latching system to our claw device and lifted up to our desired height. Once this is done, the lineman will then take the tag end of the climbing line, which is rope number 2, and attach that anchor to another rope at the base of the pole. And using a ratchet system, we're able to tighten that rope, which will keep tension on our latching system and the entire system. Kate will go into further depth, but our latching system has been designed with tension to have more force pulling that latch around the shackle. So the tension is what keeps our device from not falling down. Once this is done, the claw device can then be pulled off with our elastic friction grip, and that can be removed just leaving the rope anchored at the top of the pole. At this point, the lineman is then able to climb to their desired work height while being held in by a line the entire time. Once the lineman has finished their work and they're ready to come down, they will then take a small line of paracord and attach that to our release latch on our locking mechanism. They will then take a stapler nail and put that into the hole, which is able to stay, and run that line through it and let it fall to the base of the pole. They then are to climb down, release tension off the main line, which will then arm our release lever. Just to repeat, that release lever will not be activated or be able to move until the tension is released off our main line, making sure that there's not an accidental unlock while the line is climbing. So once they are at the ground, they release tension off the main line. Rope 4 or Lifeline then be pulled, which will open our mechanism, and that staple that the line is running through, they will fall and catch it, and then it's working as a pulley system where we can lower the rope to the ground. So the entire time the line is held in on the way up, on the way down, and the device can be safely lowered to the ground. So just a process recap, our pole and claw device will be assembled at the work site. Both ends of our latching system are going to be attached to our claw arms and lifted to our desired height. Once that claw device is closed, our latches connect, and the pole and claw device is removed, just leaving our line anchored at the top. At this point, our line can now safely climb up and get to their desired work position, which you see on the picture in the room. So process requirements, these are all things that we kept in mind throughout our entire design. All our equipment must be easily storable, transportable, and assembled by hand. Linemen already have a tremendous amount of gear that have to break to a job site, so we're trying to make sure everything's as streamlined as possible and not add to the already heavy load that they have to transport. All equipment must be resistant to weather and other elements. Linemen don't really have the luxury of waiting until after storms to do their work. They have to be out in the storms, making sure outages are at a minimum. So we have to make sure everything is able to be corrosion resistant and deal with unideal environments. For our calculations, we're considering a worker to be 250 pounds, and this will include equipment, safety gear, and wearing a first safety factor of 2 with it. Currently, we are aiming to anchor our line 30 feet up the pole and accommodate an 11-inch diameter pole. In the future, we're hoping to make this adjustable and accommodate all diameter poles. Our equipment requirements are locking mechanism. The shackle and latch needs to be easily connectable with no chance of disconnect. And I talked about the tension on the line being what is keeping our latch together. Visible indicator of the lock position, so the lineman knows that the device is ready to climb from the ground while installed. And our connection must not lower the integrity of our rope to keep up the specifications from OSHA and other organizations. Our claw system must be lightweight and easily movable when guiding up the pole, and the claw system must be able to open and release the system from the ground, leaving the rope anchored at the top.
So for the extendable pole, we are going to use hollow fiberglass tubes. This has 2 reasons. One is to keep it lightweight and still have rigidity and allow us to be able to lift it up to our desired 30 feet height. However, the second use is to make sure it is non-conductive, so in case they accidentally hit a power line, no current is directly going into the worker who is using the product. So for the calculations, we are referencing OSHA Regulation 1926.501, which states that our system must be able to survive a 250-pound worker dropping from 6 feet. This is, with this regulation, we calculate a force of around 3,061 pounds, and this will be important for the products we use later. So for the rope, we are going to use half-inch safety high-V 16-strand rope. It's stated tensile strength is 7,000 pounds, which is double our calculated force, which gives us our safety factor of 2. For the guiding claw, we are going to be making it out of a lightweight polymer, allowing us to have a lighter load when putting it up the pole, and still having the rigidity to hold the latch and the shackle. For the shackle, we are going to be using a galvanized alloy steel shackle from McMaster Carr, which had a stated capacity of 6,600 pounds, again satisfying our safety factor of 2. Here is the latch system. So the 2 holes that are on these 2 holes right here are for a spring to allow the latch system to close by itself once the shackle is in, and this one is to connect to the main rope. For the rope ratchet, we're going to use a half-inch rope ratchet from Carolina North Manufacturing. Its interior is made out of die-cast zinc and has a maximum load of 500 pounds, which is more than enough for what we are using it for. Here's a full parts list and models of all we have. This is how the rope should look in an ideal case.
So moving on to our testing plan, we're going to be doing this in 3 phases. First, we're going to start on ground, make sure all of our mechanisms work properly, the release, as well as the locking. We'll make sure everything's good before we start going up in the air. We have strength test, consistent load, and drop load test. We're going to make sure everything holds properly. As we get done that, we're going to go mid-level testing. We're using shortened pole, up only 10 feet rather than 30. Again, we're going to do the same kind of things with the locking, removing the latch from the ground, and the same stress test to make sure everything's okay. And from then on, we're going to go from full testing, full 30 feet up in the air, getting the same kind of thing, latching, releasing, stress test, good strength. Here's WBS so far. So far we have project management, design, and testing. Specifications, requirements, probably not schedule all there. As well as mechanical, rope guiding, as mentioned earlier. And for testing, just mentioned 3 phases there. As for our schedule, everything up to the design is completely accurate and it's good there. We have a tentative schedule for testing and building. We'll know exactly what's going to be there. But it's a rough idea of where we want to be for the semester. As for our budget, our bulk is taken up by the rope and the shackle is going to be a little under $200 there. But everything all together is going to be about $380. We're not certain where we're going to be able to 3D print, but it's a rough estimate. We should be around there, should be good. As for our safety concerns, obviously NSB Code of Ethics, holding the safety of others is number 1 priority for us as engineers. We also want to conduct ourselves honorably and responsibly. We're not going to cut any corner. We're going to make sure we do all this right. Make sure we don't, save for time, save for money, all by the book, all as well as we can. As for OSHA regulations, considering we're going to be being on a construction site, very, very important. OSHA regulation 1919.77, workload shall not exceed manufacturer grade. Pay attention to the rope that we've been given, the rating on that, and our own calculations and testing, so when we break things, people in the workforce are kind of have a good idea what we're doing, so they can't exceed that. They're there. Regulation 1926.2.20, safety and health regulations for construction. Obviously, a lot falls under that. We want to make sure everything's going to be safe for construction workers in the field. Upland plans for next semester. We're going to be ordering our materials very soon. We're going to 3D print the parts as needed. Like I said before, we're going to have some we have to print. We're going to assemble things and go through our 3 phases of testing. If we need to adjust anything, we'll make more prototypes, make adjustments as necessary. And we're going to consider the friction between the rope and the pole and make sure it's And here are citations. And any questions?
So what are you actually planning on building this thing?
So for the shackle, so everything besides the pole and the shackle should be of a 3D printed material or the claw and the claw, the shackle and the latch and pole should be 3D printed. The pole, the latch is going to be made out of an alloy steel, and the 3D, as I mentioned, the claw arms are going to be a polymer to try and keep it lighter. We don't know exactly what it is going to be yet, though.
So do you think the 3D printed claw is going to be able to withstand someone falling and taking the piece out?
That is one thing.
The claw device is being removed. That is only leaving the rope and the latch. So the latch system and the rope is what's taking all the force. The arms of that, the only force that is going to endure is lifting the weight from the rope and shackle to our desired climbing height. So the claw system is going to be completely removed. It's going to hold on to our latch system within the latch and friction hold. So once it's anchored and tight with tension on the bottom, the line can pull on it, and that will pull it away while leaving the line at the top of the pole.
So have you guys been in touch with any linemen?
Yes, I have some family that's in the local in New Jersey and Pennsylvania.
Okay, so make sure you stay in touch because you really need that feedback. Don't try to, because that's something for this particular project, that expertise is crucial.
Yeah, we stayed with pretty much the same, process that they would use. The only thing that we were changing is making it so we can hop over across something. We can skip that initial climb of setting the rope. The only difference is we're taking traditional climbing rope, splitting it, and adding a latch and shackle so we can activate from the ground.
What are some of the major feedback you get?
Well, currently, location of the pole, if possible, they would like to use bucket trucks, but for free climbing on remote poles or poles, like we had in our one picture, in alleys, places you can't get a bucket truck, usually the way that they climb would just be that strap and their pegs, and once they get to the top, they would then anchor themselves in, but that initial climb is done free climbing. So if you have a splinter in the wood or a device not functioning, you're going to fall with nothing really holding you.
So eventually, because there's also a second reason, which is I wouldn't expect any of you guys to test this. So you need a professional to test this.
Yes,
so
I
you
don't
need
do
to-
exactly. And for our testing, we plan on anchoring the rope, and even once we get it, 10 or 30 feet, we can still test it from the bottom. We have the rope at the ground still, so we can put loads on it while it's elevated, while still being close to the ground, so nothing will fall or drop.
But eventually, could you expect a true line manufacturer?
Yes, I have some contact with a few, and they can, we can put in another safety system beforehand so they can test it, and even while testing our system, we'll still have another one that will keep them safe.
So you sure that's your plan?
Yes.
Because we are looking forward to seeing that next semester.
Yes, no, I'm definitely going to have some professionals take a look at it and get some safe tests done on it.
Okay, and I just want to caution you, just like what Dan was talking about, any of the 3D printed materials, you can be very careful. Unless you are safe, if you just use it to hold the load, that should be okay. But you definitely don't want to use that for any those kind of.
Yeah, we also talked about reinforcing the arm.
Under the pump.
Yeah. But it shouldn't be carrying much of a load, just the weight of the rope and the latch system.
Just a quick question. So essentially the claw's the mechanism to get the rope up.
Yeah.
And then once the rope's up, you detach it, you pull it down. And then is there a constant tension then on that rope?
Yes, if you go back to 7, I think it is. So on the left here, the rope 2, that's the line that they will be attached to, and we're going to anchor that to another rope, and with a ratcheting system, we can have a constant tension on that, so there's no chance of any slack being in the line, which would, possibly unlock our latch.
Unlock it, and then when they're done, you just unratchet.
Yeah, once they come down, the tension's only going to be released once the line is safely on the ground, and we have our process for removing it safely.
Just one comment, because this is a custom project, but looks like this project is completely passive, without power system, without many things we learned. So is it possible for you to retrieve, you add a motor or something to make it automatically retrieve
That will make it easier, and also you will apply the things you learn.
We've talked about maybe replacing the rope system that activates our claw arms to close with a small motor and a wire or a bolt, so we can activate
So
that.
you can add an electrical system to your design, because otherwise you see you're missing a huge chunk of what you learn. For a certain project, you can add even more.
Okay, thank you.
Thank you.
That made me feel better. That made me feel better.
Okay, everyone, thank you for sticking around till the very end. I just have a few closing remarks. Myself and Professor Delier. Great job to all the teams. First off, thank you to the advisors that worked every week with the team. Thank you to the auxiliary advisors that were listed in the acknowledgements that didn't get credit for it, but helped the teams when they showed up at their office. Special thanks to Mitch. I know he was here earlier, but I think he said he had to leave earlier. He's a machinist, but he's much more than just a machinist. He's a mentor to these students. He's teaching them how to work safely, hands-on, great life skills they could use in their career as engineers. Fantastic. I want to thank Zach for filming. Thank you very much, Zach, from Zero Communications. I know she's not here, but thank you to Terry Shopland, the administrative assistant. She did a lot of the ordering in the last few months before we got Suzanne. But major thanks to Suzanne. Is she here? There's so much behind the scenes to make this event happen. You see the food. She coordinated with the Zebra Communications. She did much of the ordering the last couple months. She was here at 7 o'clock this morning. Her and her husband Mike went to get all the snacks and the drinks the other night at Sam's Club. They got back on campus at 6:30. So much behind the scenes. She did so much work to plan this. Thank you to our project sponsors that were here earlier. And, a lot of great projects we saw. Lastly, thanks to the students for all your hard work. This was hopefully, I said in the intro that this is, the culminating experience in the last 4 years, and really impressive projects. I know I've been talking with my colleagues, and what a great cohort. So hopefully this is something that you take with you and put on your resume. When you're going out initially into the real world, or even several years from now when you go for that senior engineering position. You can talk about these projects you worked on. So thank you to all the students. Great job. Just a couple of administrative, any of the faculty that I passed out the evaluation forms, if you could please come find me before the end. It goes towards the grade, so I'd like to tabulate that. Dr. Medora was just going to speak briefly about the FE exam. If you'd like to pass.
Just very quick announcement. Everyone, great job today. Related to the FE exam, I've been in communication with many of you. Most of you have completed it. Some of you have not. I wanted to just let you know that if you pass the FE exam, you will get a graduation award from NCEES that we will give to you at the award ceremony. So the College of Business and Engineering is holding an award ceremony on May 19th. So please let me know, because I don't know your results unless you tell me. So please let me know if you did pass the FE exam, and we will get those awards to you, invite you to the award ceremony. That's all I have to say.
And then Professor Taylor, any closing thoughts?
You've covered almost everything. I think one of the things to the students, to any family that are here, and friends of the students, they can recognize that the senior projects is a capstone issue. And in many cases, the students have had to do things beyond what their education has been in specific course curriculum. And I think that's an important issue as we go forward. We all trust that we will learn that life lesson that you have to continue learning, and you'll have to step outside the box in many cases. It's a pretty important skill that we hope you get a chance to start at your education. I think thanks to all of you. You all face some tough decisions in some cases. You face some failures and successes, but I think